Good morning. Everyone's back at it. Bright and chipper, ready to go, scholars? Very nice, very nice. Well, welcome back to day 2 of the Astronaut Scholar Technical Conference and the part 3 of the Tech Conference. It is going to be a bit of a longer program today, but I know we have great moderators. They'll make sure you get breaks in between, stretch those legs, whatever calisthenics Ashley's going to put us through today. But if you're joining us for the first time, my name is Caroline Schumacher. I'm President and CEO of the Astronaut Scholarship Foundation. Very honored to be with all these brilliant minds this week. And we're going to cap it all off tonight with a party and a celebration for you as well. You guys ready for that, aren't you? I know. Last night was just a preview. It gets way better. So we have a really special way to kick off our technical conference today. We are going to have a special presentation from Dr. Adam Weber, and he is our Neil Armstrong Award of Excellence recipient and Astronaut Scholar alum. So that will be really exciting to start off that way. But I do want to reintroduce our moderators. We have Ashley Monahan, 2018 Astronaut Scholar from Texas A&M. And ASF Board of Trustees and mentor, Carol Fitzgerald Tyler. I'll turn everything over to them so they can run through logistics, and then we'll get started. Good luck today.
Hello, hello. Are y'all excited for day number 2? Yeah. Okay. So once again, I am in charge of logistics. So for those who are speaking today, a reminder that you will have a laser pointer to point wherever you want, okay? Whenever you're clicking your slides, be sure to point towards the back, because otherwise it will not work, okay? So point it towards the AV team back there that's doing an amazing job. Can we give them a hand real quick? They have done amazingly this year. And a quick little plug. Okay, so for those of you who are Astronaut Scholars or Astronaut Scholar alumni, we have an exclusive shirt this year. So it is for the Astronaut Scholars Honor Society. Okay, so if you're interested, feel free to go in the back and purchase one. They're very nice, very gold, very demure. And thank you for laughing at my joke. I am still kind of in with the crowd. And then Carol will tell you about some other shirts and get us started.
Thank you, Ashley. Buy that shirt. Here, that's much more assertive. Buy the shirt. The shirt is nice. Okay, and speaking of shirts, well, we'll do this first. Welcome. Good morning, everybody.
Good morning.
Oh, come on. Do better than that. Give me a good morning.
Good morning.
Awesome. When I used to teach classes for ERP systems, people would say, "Good morning, Mrs. Tyler." I'm like, "Where's my mother-in-law? Where is she?" Anyway. Thank you guys so much for being here, being awake, being on time. Yesterday's sessions were amazing. My 87-year-old father agrees, just in case you wanted to know. Yes, he's very excited. He goes, "The brilliant minds in that room." I said, "Did you understand anything?" "Some." Great. So today we're going to have more brilliance, more excitement, more scholars. We will have some public service breaks, and when we say breaks, you get to go like for 5 minutes because we do want to stay on time so that you can enjoy the festivities of the rest of the day. We have Ashley, she's taking care of the tech. We'll have some timers so that you stay on time. And then here, let me model these very exciting shirts. I'm ready for some oohs and ahs. Beautiful. And I have several of these already, and they are great to travel with. And then, of course, we have this one, which I think is awesome. Very good. A trained audience at this hour. I love it. Welcome, thank you, and we'll be having a great day today. Thank you so much. I'm so sorry. I missed the memo on this. I want to welcome Dr. Adam Weber, our Neil Armstrong Award of Excellence winner for this year. He's a fantastic speaker. He's going to be talking to us about hydrogen generation and use from fundamentals to deployments. Welcome, Dr. Weber.
Thank you, and thanks for being here. I don't know about a fabulous speaker at all, but we'll try and do something. And so what I'm going to talk about is a little bit broader overview of what we do and try and give a couple of examples. I know that we have a very broad audience here in terms of expertise. And so I was an astronaut scholar in 98, 99 at Tufts University, and then moved to Berkeley, where I continued and started work in hydrogen research and fuel cells, and have continued that ever since. So I lead a group at the National Lab. So Berkeley Lab sits right above the UC Berkeley campus, and we're focused on energy conversion, and specifically electrochemical energy conversion. And so shown here, which hopefully people can see in the back of the room, is really core, but we look at kind of different technologies. So we look at fuel cells, so low temperature fuel cells and high temperature fuel cells. The opposite of that is kind of electrolysis, so where we're making hydrogen and oxygen. But then also looking at like energy storage materials, CO2 reduction, as well as some solar fuels generation. And really what we try and do in my research group is kind of meld the ability to look and understand how systems are performing. So we do a lot of diagnostics at the cell level, a lot of kind of advanced characterization at the component level, and tied together with mathematical modeling, which is what I kind of started out with my PhD research and have continued. And so we don't really do a lot of material synthesis in kind of our group. We're really just trying to understand how materials operate, kind of understand what the design rules are, and then move forward to designing newer materials. And so as I mentioned, we do a lot in kind of the fuel cell realm. So I'm not sure if everyone's familiar with a fuel cell, but really what it is you're just taking hydrogen and oxygen, and instead of doing kind of an uncontrolled combustion that you might do, for example, in an engine or a rocket, what we do is separate these into two half reactions. And so on one electrode, what we're doing is generating the protons, and then the protons can go through this ion conductive. It's a selective membrane, so it conducts ions, but it doesn't collect any kind of electrons. And so what we do is we have the protons go through, the electrons have to go through an external circuit. And as they go through this circuit, that's what kind of generates the work and generates our electricity that we can use. And then the electrons combine with oxygen and the protons across the membrane to form water at the other electrode. And really, we can start to then think about this device as kind of a fundamental architecture going forward. And so we can think of things, the opposite of this is electrolysis here, for example, where we can basically put in electricity and make hydrogen and oxygen on two selective sides. We can look at things like redox flow batteries, and so this is removing oxygen, and this is a bromine and a hydrobromic acid couple, and we do this for a variety of reasons we can discuss. We can look at things like CO2 reduction, so changing kind of the hydrogen reaction. So instead of generating hydrogen, we're taking CO2 and generating things like ethylene, carbon monoxide, and key chemicals. Or we can think of things like solar type systems, where now the electricity input is not just electrons, but really it's photons, and we're doing that to generate the electrons that we need for the reaction. And so the reason why we like this architecture is really once we start understanding at one level, it's easy to kind of leverage into these other fields and other technological platforms. And so what we say is really the platform has been explored and engineered and optimized. We kind of understand what's going on fundamentally in a lot of these systems. And so now we can start to look at other systems that are similar. It also allows us, when we want to think about something like manufacturing, kind of simultaneously going down manufacturing curves. And so although in one technology we might not be scaling up, because we're scaling up in multiple technologies, that kind of provides added benefits in terms of getting costs down. We can also guide by advanced models that can be tuned for the different reactions. And really what's critical today is selectivity. And so how do we make sure that we're being very good in terms of our material usage, our energy usage, and selectively making the products that we want? And one of the nice things about these kind of fuel cell architectures is that you have kind of inherently separations designed at the point of generation. And then finally, similar to kind of looking and scaling up, we can really, what we try to do is shorten this design, build, test, learn cycle. And so similar to kind of might argue students today or my kids, the attention span is a lot lower. And so we need to get things out and rapidly get things improved faster and faster. We're running out of time for a lot of sense. So just to take a little bit of a deeper dive of what it looks like inside one of these architectures, we showed before kind of the cell study. So you have your membrane, you have your 2 electrodes. These electrodes themselves are composite 3-dimensional structures where we have catalysts, we have ionic pathways, we have electron pathways, as well as then pore space for kind of the reactants and the products to get in. And then we can go through and look at the multiple scales all the way down to kind of, almost an atomistic length scale of where the actual catalyst interaction takes place, and start looking at kind of what is the distribution of ions, what is the distribution of electrons and species. And so what we're trying to do is it's a complex architecture, and the key is to kind of break it down to understand what goes on. If we take a step out now that we have these architectures, we can say, okay, what are we really trying to do? And that's really look at hydrogen, and this is really kind of a driver. Some people in the audience might have seen this. This has come out multiple times of what is hydrogen kind of good for. It's kind of hydrogen at scale. It started as a big idea among the national labs and then got promulgated throughout DOE, the Department of Energy. And really what we're trying to do is just highlight the fact that when we're talking hydrogen, there are multiple ways to make hydrogen. And so there are ways that we can think of using renewables, using nuclear, or even fossil fuels with hopefully some CO2 capture to generate hydrogen. Now, hydrogen is, in our sense, an energy carrier, is really what it is. It's not anything that's kind of natural. We can talk about natural hydrogen if we want. But really, it's something that we're making, and so we're taking an energy input here, converting it into some kind of commodity that we can move, we can transport, and then we're eventually going to use it in multiple applications. And so once we generate hydrogen, we can use it for transportation. And so this has been the majority of my work over the last couple of decades is in fuel cells for transportation applications. But we can look, hydrogen today is used for a lot of biomass upgrading. It's also used for biofuel production, as well as traditional fuel production. We can look at ammonia and fertilizer. So when we talk about ammonia, right, that is NH3, so it has a lot of hydrogen in there. And we want that hydrogen to be clean compared to what it is today. But then there's also chemical properties, right? It's a very good reducing agent in a reducing environment. And so when we start looking at metals production, it can actually replace a lot of the carbon that we're using in metals today as that reducing, as well as using it in things like the chemical industries. And so there's a lot of kind of uses. It's kind of the Swiss Army knife of molecules in terms of there's multiple ways to make it and there's multiple ways to use it and a lot of options there. The other reason that we're very interested in it is also it's a way to decarbonize, especially those hard to decarbonize sectors. And so things that we cannot necessarily directly electrify, we can actually start using hydrogen as that fuel. So for example, this is looking just at U.S. greenhouse gas emissions by sector. And we see that large sectors of greenhouse gases are coming from transportation. We can look both U.S. And then coming from California, a little more California-centric. And so if we replace kind of these emissions with hydrogen, which is going to be a clean, right? It really just produces water in these fuel cells as it goes through. This is a way to decarbonize. Furthermore, it's really a way to depollute, if we want to think of it that way, because as you replace the diesels, right, you're not just replacing the CO2 emissions, you're replacing the particulates, you're replacing the NOx, the SOx, and a lot of kind of the air health qualities that cause people to have lower lifespans in neighborhoods around high transportation corridors. And so we really see hydrogen as that agent to be able to do that. Of course, we have to bring down costs. We have to be able to do this efficiently and without too much burden. And so how do we do that at the national lab? So across the lab, what we look at is across what we call a TRL scale. So this is a technology readiness scale. You can think of this from kind of basic science to applied science. And really, as I said, that kind of increasing that cycle of the design, build, test, learn is really also going across these TRLs simultaneously if you can. And so we have programs from very basic science of understanding fundamentals of solar fuel conversion or electrolysis, up to kind of the applied programs, for example, looking at fuel cells for trucks or water electrolyzers, all the way up to, I'll touch on this a little bit later, to a hydrogen hub and really pure deployment kind of exercises. And our tagline for kind of the research is systematic research to solve applied problems, but it's really informed by analysis, right? Once again, we don't have a lot of time, so we want to make sure that we're working on the problems we need to work on today. And so as an example of that, what you see here is some techno-economic analysis. So here we're looking at kind of where the drivers and where the levers are going to be to reach lower costs for hydrogen generation in this case. And so this is driven a lot by the hydrogen energy Earthshot. If people have heard of this, this is kind of the moonshot from Kennedy, but looking at it from different technologies on the energy side. And so really it is to get to $1 per kilogram in 1 decade, or actually 9 years now since this was done last year. And so how do we actually do that? We can do some analysis, and what we see is, sure, as we start to scale up, there are things that are going to be increasing in terms of being able to decrease the amount of time looking at the scale up, but really we have to increase the lifetimes, we have to increase the efficiencies, and we have to kind of decrease the capital costs. And a lot of that is really due to innovation. Today's technology will not actually allow us to meet this energy Earthshot, and so we need to figure out ways to improve it. So the way that we go about it in my group is looking at kind of this mathematical modeling type framework to where we're trying to explore the underlying physics, where we have kind of in a model, you have complete spatial and temporal evaluation of mass, energy, all those types of flows. We use modeling to help interpret experimental data, really elucidate or uncover kind of the controlling phenomena and bottlenecks, and especially looking once again at things that are not experimentally accessible today. You can also then start to think of kind of virtual experiments, looking at sensitivities, defining operating conditions, examining different architectures and trade-offs, and helping guide kind of materials integration. So what is continuum modeling? For those who don't know, it's really just treating things as a continuum. So from the quantum or the statistical mechanics or molecular dynamics, we look at discrete particles. At the continuum, we kind of wrap all those up into things like concentrations, probabilities, and overall driving forces and fluxes. And then look at the higher levels, then you can look at kind of complete system models. So if we take kind of what our modeling can do, we can look at different architectures again. So looking at the fuel cell or water electrolyzer of both an acidic or an alkaline type, we can then use that modeling to really break it down into what is actually causing the losses. So for example, this is what we call a polarization curve. So this is cell potential versus current density. And really, we want this to go out as far as we can. So for a given cell potential, we're getting more and more current. And what we can do with the modeling is kind of break this down to, how much is actually kinetics, how much are ohmic or just the ion movement, how much is the mass transport or the reactant movement. And then we can go through and figure out how to make each of these losses smaller. Similarly, in both the PEM and the hydroxide water electrolyzers, once again, you get your overall polarization curve, where again, you want to push the current density out for as small amount of potential as you can. And what you see here then is dominated by ohmic, dominated by kinetics. Here it's a little bit more complicated because we also have 2 different types of kinetic mechanisms dominating. So this is just to give you a flavor for what we're trying to do with the modeling, right? Really trying to break things down to understand what the limitations are in the system. And so I'll end with kind of 2 quick examples and then take questions. So one is looking at microporous layers. I like this example because it's one of the rare examples where the modeling actually came much further and before the experiments. And so what we see here is really what we want to do is increase the oxygen partial pressure for a given amount of capillary pressure. So think of this as just a water pressure, and then you're going to flood the system as you go to higher water pressures. As you flood a material, it's harder to get the oxygen. And what we saw is if you take kind of a traditional signature and look and add some hydrophilic pathways, we can start to increase the amount of oxygen we get for a given capillary pressure. And so if we add some of these kind of hydraulic pathways, that seems to increase the performance by decreasing the amount of water in the system. And so this was, we did this work in 2010. And then, as I mentioned, about 5 to 8 years later, we actually got experimental proof of this. And so this is shown here in terms of the overall polarization, where we see here as we move towards adding something with hydrophilic pathways, we're getting increased performance, and shown here. And then, once again, what we do and kind of understand this, we look at kind of different diagnostics. So this is some neutron imaging to look at the amount of water within a cell. This is some nano X-ray computed tomography. Once again, we can look at the water pathways here. And so what we see is, indeed, when we added these kind of hydrophilic pathways, they fill up with water in these systems, and that actually decreases the amount of water overall in the system, which gives us kind of better performance. And so once again, it's a way that we can use modeling to help guide what should be materials integration. The final example I just want to show going across scales and kind of unintended consequences. And so what we look at is not just performance, but also lifetime. And so one of the big advantages for fuel cells that allowed us to go from kind of tens of hours to tens of thousands of hours was a serendipitous finding from both Asahi Glass and Toyota that if you add kind of cerium in the membrane, it acts as a radical scavenger. And so basically there's an attack, a chemical attack, and you can reduce the amount of the attacking agents by adding cerium. This was done completely by accident just because the guy who was working on membranes, his wife worked with car components and had some cerium lying around, and so they said, why not? Let's just toss it in, see what happens. And lo and behold, here we are now with vehicles on the road today, one of which I actually have. And so if we look, what happens is, we can look, and when we add cerium, it changes the properties of the materials in the membranes themselves. It changes the domain spacing, so it changes the morphology, which changes some of the things like conductivity, so how well it conducts ions, changes things like its water uptake. And so we have this experimental data. This becomes an input into a nanoscale model to where we're trying to understand these different interactions on this scale, and then can scale this up to a mesoscale to where now we can actually start to look at what the ionic and water pathways are. And so once again, this is experimentally not achievable today. And so then we turn to the modeling to help kind of explain what goes on in optimization. And so what's interesting, though, is when we go up to the macro scale, we do see that there are trade-offs. And these are trade-offs that haven't necessarily been thought about. So yes, as we increase the amount of cerium, our time to failure will greatly increase. And so we see that. But interestingly, if we have too much cerium, this actually causes performance losses because of the way it changes the pathways, because of the way it changes the properties. And so once you see kind of unintended consequences, and there's always kind of these Goldilocks scenarios. And so that's what I really like to try and get at in terms of my modeling, is really trying to understand that optimization, right? We typically have two forcing functions, and we have to find what the critical point is and find those boundaries. So in summary, what I've tried to say is, as we start to electrify things, fuel cells and related electrochemical technology platforms are really going to be a foundation for 21st century technologies. If anybody know Harry Gray from Caltech, he once said at a National Academy meeting that electrochemistry is to the 21st century what thermal chemistry was to the 20th century, right? Really, we're moving to an electrified environment. And so starting to understand how these actually interact is going to be critical. We need to look holistically at limiting phenomena, look at both kind of combined performance, durability, increasing our innovation cycle times. And we believe, and I've shown hopefully that continuum modeling can be really powerful toolbox in kind of that understanding. And so with that, I just want to give you guys a flavor for kind of my research. Also thank kind of the energy conversion group for a lot of those who provided input into this research and kind of that larger group, and take any questions. Thank you.
Thank you so very much. We have time for one question right now.
Hi. I was wondering, when you're using hydrogen fuel cells in cars, you need to have refueling stations and sort of what that infrastructure is going to look like and how safety concerns are going to affect that.
Sure, and so that gets to kind of the deployment side of things. Of how do we actually do a rollout of a hydrogen infrastructure, such that you have stations, you have trucks and cars, and you have hydrogen all there at the same time. And so once again, if you take a systems analysis standpoint, you can actually start to meld those over time, understand where your hydrogen is being produced, where it's going to come. In terms of safety, a lot of this, and this has been shown, that hydrogen has been used for decades and tens of decades in terms of a lot of in the petrochemical industry. There are hydrogen pipelines. In the Gulf Coast, for example, there are thousands of miles of hydrogen pipelines. And at stations, we can start to understand how to utilize that. It's no worse. Actually, it's often safer than gasoline in terms of it doesn't spread. In terms it typically just evaporates. And so there are safety protocols that are out there to kind of understand.
Okay, thank you.
Thank you. And for more questions, which I'm sure you have, please find Adam later. But thank you so much, Adam. All right, we would love to welcome Stephen Argauer to the presentation on characterization of the photophysical properties of AU complexes. Welcome, Stephen.
Hello, my name is Stephen Argauer. I'm studying chemistry at Virginia Tech. Doing Air Force ROTC, I had the opportunity to attend the Air Force Academy for one semester on exchange while I was at the Air Force Academy. I was able to do research, so although I only did it for one semester, I just wanted to show you all a little bit about that research and what we did at the Air Force Academy. First, we will be talking a little bit about the triplet state, then we will go into the experiments that were conducted and the characteristics of the compounds that we studied, and then I would like to talk about the future research in this area. So with that, let's talk about the triplet state a little bit. So over on the left here, we have the singlet state. This is the ground state that all molecules start in. When you shoot a molecule with a laser, it will be excited into the singlet excited state. Sometimes molecules can go from the singlet excited state to the triplet excited state. Now, what's cool about the triplet excited state is that paired electrons must have the same spin, or must have opposite spins. So if you see in the singlet ground state, these arrows, which represent electrons, have opposite spin. When the electrons have the same spin, it prevents the molecule from going from the triplet state back into the singlet state. So while it's in the triplet state, it gets stuck in the triplet state for a few microseconds, and in those few microseconds, we are able to study these compounds. Specifically, we are studying the fluorescence of these compounds from the triplet state to the singlet state. Since there's a delay, since they stay stuck in the triplet state for a second, the fluorescence is delayed, and that is the fluorescence that we are studying in our research. This here is a much more complicated diagram of what we had on the previous page. This here represents the molecule that we have. So we shoot our compound with a laser. It gets excited into the singlet state. The idea is that it has intersystem crossing into the triplet state, and then fluoresces back to the ground state. That is what we are trying to study. However, there are other ways that these molecules can be reduced down to the ground state. One of them is fluorescence from the excited singlet state. Once the molecules are excited, they're in the excited singlet state, and they can go back down into the ground state. We put gold in the compounds because it encourages intersystem crossing into the triplet state. Another problem that we had with studying these molecules in the triplet state is that oxygen is naturally in the triplet state, and there's a little bit of oxygen in the air. So it would quench the molecules from the triplet state. To remove this problem, we would freeze, pump, thaw our molecules. So we would freeze our solution, pump all the air out, and this would remove all the oxygen and would keep the molecules in the triplet state for a longer duration. The third and final problem that we have is triplet annihilation. This happens when two molecules in the triplet state find each other, one of them will be excited into a higher level singlet state and then non-radiatively be reduced to the ground state, while the other one is reduced directly to the ground state. To reduce this problem, we have a low concentration of molecules so that they don't find each other as often, and we can study these molecules in the triplet state most effectively. So the procedure that we did, we dissolved this molecule here. This is the molecule that we studied. Notice how it has gold in the compound to encourage intrasystem crossing into the triplet state. So we dissolved it in toluene. We were looking for absorbance about 0.8. This was a low enough concentration that triplet annihilation was not that big of a problem. Then we would freeze pump thaw our compounds. Then we shot the compound with a diode laser from a xenon lamp at 385 nanometers. Notice that 385 nanometers is a non-visible light. So we would shoot it at 385 nanometers. Then we would analyze the absorption spectra, emission spectra, and kinetics in the triplet state. Let's talk about that a little bit more. So the two things that we studied were the kinetics. How long did it stay in the triplet state? The second thing that we studied was the emission spectrum. So over here, we have the emission spectrum of the molecules from being excited into the triplet state. Our goal was to find a compound that absorbs non-visible light, so that 385 nanometers. And in the singlet state, it would absorb non-visible light. But then in the triplet state, it has a different absorption spectrum. And the goal was to absorb visible light while it was in that brief moment in the triplet state. Future research is to find a way to put our molecule, BTF0, into a solid matrix for military applications. I will now be taking questions.
Thank you, Stephen. Who has a question for Stephen? It's a race.
Hi, great job. So you mentioned that you're using a laser to probe these properties, and there's so many different chemical techniques to probe metal complexes. Has there been any other work using X-rays to probe these structures?
Not that I know of at the moment. Most of our research was involved with analyzing after the laser shot, so they had done lots of research on what laser would be ideal for this compound. So our research was focused on what to do after we shoot the laser with the compound.
Can you speak more about the solid matrix for military applications?
I can't, I'm sorry.
I understand.
Or bad things will happen. Okay, thank you so much, Stephen. All right, next, let's welcome Peter Valet on reinforcement learning applied to in silico process controller parameter tuning. Welcome, Peter.
Good morning, everybody. My name is Peter Valet, and I'm working at LSU's Process Systems Engineering Group with Jose Romanoli and Cal Torito, working on computational applications to chemical engineering. So today I'll be talking about some work we're doing in the lab regarding applications of reinforcement learning to tuning computationally simulated chemical engineering plants. So first, I'll talk about the natural gas liquefaction plant that we created in our lab and computationally simulated using Aspen HYSYS. And I'll be talking about the algorithms relating to reinforcement learning that we also set up using open source platforms such as Python and Stable Baselines 3. So in chemical engineering, a common reason for setting up a chemical manufacturing site is to take raw, cheap material and to sell it and separate out or manufacture more expensive materials for selling on a market for a higher price. So in this case, we have a natural gas liquefaction plant that takes in raw natural gas and separates out, methane and ethane for selling on the market. So within the natural gas liquefaction plant, we have a number of process variables that need to be controlled for steady state operation and for efficient, cost-effective production. Some of these include temperature, composition, flow rate. So you can see here, we have a number of controllers that control either valves or different parts of the process that are based on control theory and well-known PID or proportional integral derivative controllers. So using this computationally simulated plant in Aspen HYSYS, which is a well-used and industry standard tool that can dynamically simulate the chemical plant, we created a Python connection to it to control the parameters within PNID controllers within this plant. So within traditional process control, if you wanted to set a set point, such as a temperature or a composition that you'd like to see in your plant, you would have this, or the set point would be sent to the controller, which would then determine the actions regarding the plant. And once it would observe the disturbances and the response to the actions, it would then adapt and decide on the next action to maintain control within a chemical plant. So reinforcement learning could be useful here for determining the parameters of the controller and which determine the performance of the controller. So traditionally, we've seen in robotics that reinforcement learning has been used for adaptive learning for example, the landing of a lunar lander or the stability of a hammer swinging on a cart. So in this case, instead of a moving robotics case, we're trying to see if reinforcement learning could be used to learn the optimal parameters of controllers within chemical plants. So in this case, we would replace the parameters within the controller with active learning and trained parameters that can be seen and interact with the chemical environment to determine the optimal parameters such as gain and time derivative, or KC and TI, within the controller. So in this case, we'd have an agent interact with the chemical environment, test and find optimal parameters by suggesting either at first random gain and time derivative, and then later on, after seeing the search space, and then begin to understand what's the optimal parameters. So this agent would interact with our environment, learn from a reward function that we've set up, and then be able to start guessing better and better process parameters for better performance within the chemical plant. So in this case, we have two parameters that we're looking to search initially, our gain and time derivative. And they have a limited spectrum because at the boundaries of the spectrum, you can see worse performance and perhaps dangerous performance within a chemical plant, which will lead to unsteady state operation, otherwise dangerous operation. So we set boundaries within these two parameters, and we'll allow our agent to suggest only actions within the boundaries. Our agent is allowed to see the current operation and the previous operations of the chemical plant to be able to learn what's the most optimal performance for the controller parameters suggested. And then it is also allowed to see the integral squared error of its performance profile after it has suggested the new action. So you can see here the integral square error is the difference between the desired set point and the current operating point of the chemical plant. So you want the operating point and the set point to be as close as possible. So our agent sees the integral square error and tries to minimize it after suggesting multiple runs. So we decided to start off with the simplest case, which is a single set point change in disturbance within a chemical plant, and to see if the agent could learn by suggesting desired parameters within the simulation. So we have here our set point would change once from the initial starting point, and we would repeat this experiment over and over again until our agent begins to suggest the optimal parameters for controller tuning. Here. And so our results, we found that it was able to learn the optimal, or at least improving parameters for the search space. And it could maximize the total reward in the long term. And as you see here, it suggests initially worse parameters, but then begins to learn and change its suggestions to lead to more optimal parameters for the controller tuning. Yep. I'll be taking questions. Thank you.
Thank you, Peter. We have time for one question for Peter. One.
So this is really awesome control stuff. How are you going to deal with noise from the observable state?
Yeah, so one of the problems we're actually seeing is that Aspen hysis has an underlying randomness that we're unable to tap in or control the seed of. So we're thinking that the noise can be kind of smoothed out by multiple runs at the same suggested parameters. And we're hoping to take maybe a mean or otherwise smooth out the testing of the noise. Yep.
Thank you so much.
Thank you.
So going forward, just a quick announcement. So if a scholar is asking a question, it would be great if they could stand up while they're asking it so we can get some good visuals on you. Thank you. Sage Martin is our next presenter, the role of underlayer materials in achieving organic spontaneous orientation polarization. Ha, 9:45.
Hi, everybody. My name is Sage. I'm from the University of Minnesota. And as Carol said, I'm presenting on the role of underlayer materials in achieving organic spontaneous orientation polarization. My mentor for this project is Yevgeny, and our PI leading this project is Professor Russell Holmes. If within the past decade you've been looking to purchase a TV or a new smartphone, you may have seen the term OLED appear. And so these devices differ from traditional LEDs in the fact that they use organic materials rather than inorganic materials like silicon or germanium as their light emitting sources. So if you notice here, these are what these organic materials sometimes look like. Sometimes they're metal or complexes, as Stephen was mentioning. Thank you. So I don't have to go through all that here. But if you can see here, these OLED materials, just like LEDs, are usually a big layer stack. And once you apply voltage across this layer stack, you eventually emit light through fluorescence. And so what our group is particularly interested in, and especially the focus of this project, is to study what happens in each layers and how are these molecules aligned. And what we've noticed is that when you have an OLED molecule that contains an electrical dipole, it'll actually, as it's being deposited from the vapor phase, it will actually spontaneously orientate itself to sort of create a net dipole or a net potential effect across the whole film. So as these molecules approach our film, they kind of twist and arrange themselves to create a net electrical effect. And so the way that we're able to measure this is through what's called a giant surface potential. And this giant surface potential actually increases linearly with the thickness of our film. And so using the slope of that relationship, we can actually obtain a comparison to study a lot of different materials and see how strong is this orientation effect. Now, generally for OLEDs, this effect or this spontaneous orientation is actually not desirable. It can actually limit the efficiency of our devices, but there are other device systems using organics like electric generators that can actually harvest this permanent polarization and actually generate current from it. And so the core question we're seeking to ask is, how does the strength of this effect vary with the underlayer material or the underlayer material's work function more specifically? So we're interested in this molecule here as our thin film or as our SOP layer. This is ALQ3. And then we have various underlayers, including aluminum, gold, and molybdenum oxide to adjust our work function. And I'll explain that a little bit more about that later. The way that we actually make our devices is a process called thermal evaporation deposition. This was covered by Santiago yesterday, but as a recap, we have a chamber at a low enough pressure such that when we heat up our material from a solid form, it actually vaporizes and sublimates into a gas. This gas then floats up to our substrate, and the substrate eventually captures it as a thin film. The way that we measure our surface potential is through a method called Kelvin probe, and our Kelvin probe is an oscillatory probe technique that is able to essentially measure our work function of a normal metal, but we're also able to apply it to an organic film as well. So as far as our results, I wanted to first discuss why molybdenum oxide is so important. And so if you notice at this graph, as you increase molybdenum oxide's thickness as an underlayer, it will actually increase the work function monotonically. And so at first you get that sharp rise in work function, and then it kind of levels off into kind of a more constant logarithmic work function. And what we've noticed here is that when measuring the surface potential of our ALQ3 film, if you notice around that 110 nanometer mark or so, we see that as you increase molybdenum oxide thickness, our surface potential also increases. And when you map that using that slope technique I was discussing a little earlier, you can find that at lower work functions, you get sort of like a slow and steady rise of that GSPS or that slope. And then at this specific underlayer work function, here it's around 4.5 EV or so, you get a sharp rise, and then your slope kind of snaps into place, and it no longer is dependent on underlayer work function. So from these results, we can actually develop a charge injection theory. So this is mapping out how our electrons are moving between our layers in our device to understand why this is occurring. We're also trying to implement computational and machine learning models to actually predict where this might occur. And finally, we're also studying different charge injection methods. So traditionally, we're using electrons from a cathode or electrode, but now we're trying to study, can we actually capture light and photovoltaically produce electrons to then study that behavior. All right, thank you so much.
Oh, thank you, Sage. Let's take a question, please. And if you're a scholar, you know what to do. Any questions for Sage?
Hey, Sage, great talk. Why do we? I'm not a scholar. I'm an alum. That's okay. So why do we? Why organic materials? Like, what's the benefit of using those instead of just the classic LEDs?
Yeah, that's a great question. So traditionally, OLEDs are usually seen, you may have seen in advertisements, they advertise better color accuracy. So what's a defining feature of OLED materials is that when you actually turn the device off, you're able to produce kind of like a true black. That's actually one of the major benefits. OLEDs also have the potential for greater device efficiency, and then also OLEDs being organic, they can actually be petroleum derived or produced much easier or synthesized much easier compared to synthetic materials that require like mining or more intense processing techniques. But so whenever you see those, and also actually, I forgot to add, OLEDs are very popular for curved displays. So rather than using like a brittle crystalline silicon, you can actually use organic materials to create those curved displays. And actually, other groups are working on mechanical properties to make those flexible displays even more flexible than what's previously seen.
Wonderful. Thank you so much, Sage. I hate it when your slope has snapped, so we have to avoid that going forward. Jack Verich, we welcome you. Amplifying ionic liquid electrolyte capacitance with metal salt addition. Welcome.
Thank you. So I'm Jack Verich, and today I'll be talking about ionic liquid electrolytes and specifically improving their capacitance. So a little bit of an overview why I think my project is important. As we continue to adopt more renewable energy technologies, there's a need to develop robust grid-scale energy storage because these renewable energy sources are intermittent and variable in nature. And an ideal candidate for these systems is the electrochemical supercapacitor because it has high power density, fast charging discharge kinetics, as well as cycle lifetime when compared to the traditional lithium-ion battery. And specifically, for these systems, looking at ionic liquid electrolytes opposed to organic-based electrolytes because they have a wide potential stability window and are much safer, non-flammable. So when we look at the energy that you can store within a ideal capacitor, as shown on the screen here, that voltage window has a squared relationship with the energy stored. However, because these species are ionic compounds, liquid at room temperature, they're highly coordinated in nature, and as a result, are poor at screening surface charge on electrodes, and as a result, do not have very high capacitances. So my group proposes that by adding metal salts to these systems, we can use a new method of capacitance known as pseudocapacitance to basic reversible reaction between metal ions and the electrode surface to increase the capacitance of our device and as a result make these more energy dense devices. So looking a little bit into my work, we use a well-characterized ionic liquid beam MTFSI and make metal salt and ionic liquid mixtures with salts of varying ionic radii, charge valency, as well as concentration. And then all of our mixtures are characterized using electrochemical impedance spectroscopy. So essentially what that does is applies an AC voltage bias to the system and then measures the current response. And with that data, we can apply it to a model and then get the capacitance of our material. And then also we pair that with Raman spectroscopy to understand how ion aggregates change at varying potentials and how that influences the capacitance of our devices. So the ionic liquid we use, it's kind of hard to see on the screen, but it's shown here. So the cation is this blue structure, and then the anion is the red one here. And then looking at our results, we found something really interesting. So we see a huge improvement in capacitance at high polarizations, high negative polarizations, which was expected for the monovalent small ions. Essentially what is happening is these small cations are coordinating with the ionic liquid, breaking up these neutral aggregates, which we confirm through the Raman spectroscopy, packing at the electrode surface, and adding that pseudocapacitance contribution to the system. We do not see the same case for potassium. We believe that potassium does not have an affinity to the electrode materials that we use. Thus, there's no added capacitance influence on top of what already occurs through the double layer capacitance. And then for our multivalent cation, which is magnesium, we actually see a decrease in capacitance at all potentials, and we believe that this arises from magnesium actually coordinating with more ionic liquid ions in the system, creating larger structures, and is less effective at screening charge on that electrode surface. And then also, not as clear of a trend with how concentration of these metal and salt mixtures affect the system, but we do believe that there's altering in the nanostructuring of our ionic liquid aggregates as you continue to increase the charge, the concentration. So yeah, this is kind of that area of importance to us. So looking forward, we hope to build asymmetrical electrochemical supercapacitors to test this on a deeper level, and we do think that this is a promising option for energy storage because we are able to significantly increase the capacitance of these materials and operate them at a larger voltage window than seen before. So thank you all.
Thank you, Jack. Who has a question? There's a question.
Just like bigger picture, like looking at a timeline, like when do you see these being implemented into like devices that people are going to be using?
Yeah, so our group has already submitted a patent application for these salt and ionic liquid mixtures, and we're already working on building these like small coin cells. So I guess optimistically, I think within the decade, we'll see more and more of these electrochemical supercapacitors be implemented. And it is needed if we hope to reach these decarbonization goals within the next few decades.
Thank you so much, Jack. Let's please welcome Curtis Allhouse. Cleaner, greener, and colder 3D printed aqueous zinc ion batteries. I changed your title to make it hotter.
You killed the presentation. You killed the pronunciation. You got it. Hello, everybody. My name is Curtis Althouse. I am a senior at the University of Illinois studying chemistry and astrophysics, and today I'm going to talk to you about batteries. Batteries are in everything from your laptop to your phone to your TV. We use lithium-ion batteries almost across the board, and unfortunately, lithium-ion batteries are flammable and can combust. They're expensive, and they're also bad for the environment. So finding alternatives to that is really important. as we go forward with limited reserves of lithium ions. And so yeah, that's what we're trying to do at Lawrence Livermore. So the system that we're working with is called a zinc manganese oxide battery. This uses zinc as an anode, which is a metal, and manganese oxide as a cathode. As we apply reductive potentials, zinc goes inside of the manganese oxide, and as we apply oxidative potentials, it leaves. Thus, it serves as a battery. So there are a few reasons why aqueous zinc-ion batteries are really great. For one, the electrolytes are made out of water, and water is largely non-flammable, which is great. Another thing is zinc manganese oxide batteries are extremely inexpensive, and we have tons of zinc and we have tons of manganese, and so that makes for better batteries. Now, what's the catch? The catch is that because we have a metal anode, we're prone to forming something called dendrites. Dendrites are little spikes of zinc that, as we cycle our battery, can get larger, and eventually we can get catastrophic dendrite growth, which shorts your battery and your battery ceases to be a battery. Now, finding a way to improve the performance of these batteries while minimizing dendrite growth is really the key to making these specific battery systems work. And the way that we want to do that is by manipulating the geometry. Typical batteries have what are called a parallel plate geometry. This is a cathode and an anode that are parallel to each other, separated by a separator with electrolyte in between. And these geometries are really easy to make, but they're actually not as efficient as they could be. We can actually use our space more efficiently with interpenetrating geometries, like the one up on the right. And with these, we can get all sorts of benefits, like enhanced design freedom, smaller diffusion distances, which is important for low temperature work, high energy and power density, which is great for faster cycling and better capacitance, and also balanced electric fields, which for the dendrites I mentioned before is extremely important. So I had this great analogy about parking lots and cars, but all you need to know is that for the same amount of volume, we can get better capacitance and faster cycling from our batteries. So how do we go about making these 3D printed batteries? We start with Pusel printing, which is projection microstereolithography. We have a dunk tank with resin, and we bring a metal tray up, and we shock it with a laser, and it forms the resin into the structure that we want. Now, when we take these 3D structures out, they're made of plastic, and they're also pretty flimsy. So we stick them in an oven, and we roast them for 3 hours. Now, with these 3D batteries, they're made of plastic, so they're non-conductive, which means we can't deposit battery materials on them quite yet. So we use a process called nickel electrolysis deposition, which basically seeds growth on these 3D printed batteries and grows this gorgeous nickel film. And with this nickel film, we can deposit our battery materials. Now, unfortunately, the anode and the cathode are interpenetrating, like I mentioned before, and that means that we can't actually remove them from each other. So we had to come up with a way to co-deposit our battery materials, which basically means we're depositing our zinc and our manganese oxide at the exact same time, and that is really, really tough. But what we were able to prove through this process is that we can take a 3D printed structure, and this could be any 3D printed structure, not just the one that we came up with. We can make it conductive, and we can deposit battery materials on it. Now, this work is still ongoing, and we're actually in the process of testing these 3D printed batteries to actually see whether our performance is better than conventional battery geometries. And so that's something we're working on right now. In addition to that, we want to actually apply these 3D printed geometries to other battery systems. Lithium-ion batteries are great, and they have their benefits. So can these geometries still benefit those systems and improve the batteries that we have today? And with that, I would like to thank ASF for having me to present for another year, and I would like to thank all of my mentors, and I would love to take any questions that you may have.
Thank you so much. Questions?
How did you choose the elements that you did for the anode and cathode?
That's a great question. So let me back up. So we needed, in order to do this co-deposition, we needed an anode that would reduce and a cathode that would oxidize, so we can do this thing in a loop at the exact same time. And manganese oxide is not just a great cathode material for zinc, but also for lithium ions. And so we wanted a cathode that would work for a bunch of different systems so we could scale this up. So that's why we chose what we did, but it could be applied to other types of batteries, not just this one. Yeah.
Thank you so much, Curtis. So, two very quick announcements. So we have so many people here today. We want you to snuggle, squish together so that more people can fit in. That's it. Everybody squish, squish. So more people can come in. Please come in. There's seating right in the front row. We don't bite, I promise. The second public service announcement after you squish is the hotel is now aware of the fact that water is largely non-flammable in the pool. So with that, let's welcome, please squish, please come forward and squish, Aidan Lindsay, Active Learning of Electronic Coupling in Doped Organic Semiconductors. Welcome, Aidan.
Okay, hello everyone. My name is Aidan. I work in Professor Nick Jackson's group, also at the University of Illinois, and my project is titled Active Learning of Electronic Couplings in Doped Organic Semiconductors. So semiconductors have without a doubt revolutionized electronics in the past 100 years, and have affected a variety of important industries that impact our everyday lives. And semiconductors have been able to achieve this large level of commercial success due to doping, which has greatly increased their conductivities and made them better for applications in modern electronics. Now, organic semiconductors, or OSCs, have recently emerged as cheaper, more lightweight, and more flexible alternatives to traditional inorganic semiconductors that you see everywhere today. However, their main drawback is they require about 5 orders of magnitude more dopant to be as conductive. So the figure on the left shows your typical OSC, organic semiconductor, as illustrated by these long folded polymer chains. And when you introduce a dopant into the structure, the dopant will oftentimes get a negative charge and it will induce positively charged holes throughout the OSC. And this is how this organic semiconductor actually transports charge throughout its structure. And the fact that organic semiconductors require so much more dopant leads to significant morphological, meaning structural, disorder within the OSC, and this can further inhibit charge transport. So when an organic semiconductor is doped, there are 2 distinct doping mechanisms that occur. The first is integer charge transfer, in which an electron from the highest occupied molecular orbital of the OSC is donated to the lowest unoccupied molecular orbital of the dopant. And there's also charge transfer complex formation. And here, the molecular orbitals of the OSC and the dopant overlap to form this hybrid charge transfer complex in which partial charge transfer occurs. So the key question that my project is trying to answer is, how does morphology affect the electrical conductivity in these doped OSCs? And so to do this, I'm creating a machine learning model that can reliably predict the charge transfer mechanism, so integer charge transfer or charge transfer complex formation, in OSC dopant pairs based on their structure. And to do this, my model will be predicting electronic couplings in these pairs, because a strong electronic coupling typically corresponds to charge transfer complex formation. So the first step in any machine learning problem is to establish your data set. So to establish my data set, I ran molecular dynamics simulations of P3HT, which is my organic semiconductor, and F4TCQ, which is my dopant. So in molecular dynamics, you're essentially putting molecules in a box in a particular thermodynamic ensemble, and you're letting it run until it reaches thermally equilibrated conformations. And so after running my MD simulations, I extracted about 600,000 OSC dopant pairs to establish my data set. And this is an example of a particular OSC dopant pair. So you can see right here, that's F4TCQ, our dopant, and just below that is P3HT, a monomer of it, which is our organic semiconductor. And quantum chemistry calculations were run on this particular OSC dopant pair to show the HOMO, the highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital. So the next step in my project is to featurize the structure of these OSC dopant pairs. So I have to find a way to somehow encode the structure of these pairs into numerical vectors, which I will then feed into my neural network. So to do this, for each OSC dopant pair, I constructed a distance matrix. So every entry in the distance matrix is a distance between a particular heavy atom in the OSC, the P3HT monomer, and the dopant, the F4TCQ molecule. I then flattened this into a feature vector, and then we did principal component analysis on it on the first 15 principal components, as 15 principal components describes more than 95% of the variance. And so for each OSC dopant pair in my data set, I had a 15-dimensional feature vector. And then also for the targets that I'm trying to learn, we use quantum chemistry to calculate the ground truth electronic coupling values. And so now I can actually do some machine learning. So the workflow I used was an active learning workflow. And in this workflow, you have your machine learning model, which in my case is a deep neural network. And you will start out by training your model on a small subset of your data. So for me, that's about 3,000 to 4,000 OSC dopant pairs. And then you will use that model to estimate uncertainty on the other pairs that are not in your training set. So we use evidential regression for that. If you're interested in like uncertainty quantification, you can ask me about that later. But we estimate the uncertainty, and we take the pairs with the highest uncertainty and add that to our training set. And when we're adding it to our training set, we also calculate the ground truth electronic coupling values using quantum chemistry, and then we will retrain the model. So each loop of active learning will improve the performance of the model. And the main goal of active learning is essentially to get as accurate of a model as possible using as little data as possible. So for some actual results from our active learning model, the highest uncertainty plot, you can see that this is a plot of the R-squared score, which is a measure of how effective our model is, versus the percentage of training data. So each point on this plot is another active learning iteration that we did. And so we compared this to a random search baseline. So the highest uncertainty plot is our method of choosing the OSC dopant pairs that have the highest uncertainty to add to the training set for each active learning loop. And random search is our baseline. So instead of using highest uncertainty, we are just randomly adding OSC dopant pairs to our model. And you can see that our active learning method using highest uncertainty greatly outperforms the random search baseline, and it tops out at above about 20% of the training data, and the R-squared is above 0.8, which shows that our model is effective and reliable at predicting these electronic couplings. So in conclusion, a data set of organic semiconductor dopant pairs was constructed via molecular dynamics simulations using quantum chemistry for the target values. We built a neural network model that was effective at predicting these electronic couplings, and the active learning scheme that we employed outperformed our random search baseline. So I would like to thank my PI, Professor Jackson, my mentor, Dr. Chuni Wong, the rest of the Jackson Group, pictured here, and the Astronaut Scholarship Foundation. And I'll be taking any questions. Thank you.
Thank you, Aiden. We do have time for one question for Aiden. If you're a scholar, stand up. There we go.
Really fascinating. I was curious where you think the positive charge localizes on your membrane species. And also, those are some really complex homos and lumos. Have you looked into possibly modeling interactions with other dopants that might have more geometrically accessible overlap?
Great question. So for the localization of the positive charge, we didn't look into that more than just like positively charged holes are essentially generated like within the folds of our OSC. And also, our data set consisted of monomers of our OSC. So we didn't actually look at like the full like P3HT chains that you would see in an actual OSC. So it was more difficult for us to actually see like where that charge localizes. And yeah, the homos and lumos are pretty complex. Mostly what we were using that for was just the overlap. So we were using the overlap of the homo and lumo for our electronic coupling values. So it's a good thought to try other types of dopants, but P3HT and F14CQ is like a very common, I guess, OSC dopant pair. And we essentially want this paper to be like a methods paper of like someone who's fitting electronic couplings in the future would like look at our paper and see like the best practices for how to do that. So thank you for the question.
Aiden, thank you so much. We would now like to welcome Kennedy West, synthesis of titanium oxynitride for photocatalytic activity in visible light. Welcome, Kennedy.
Hello, my name is Kennedy West, and I attend the #1 public HBCU in the nation, the illustrious North Carolina Agricultural and Technical State University. And today I will be presenting to you the synthesis of titanium oxynitride for photocatalytic activity in visible light. So a little bit more about me. I'm a graduating senior studying chemistry. I am also a part of the Honors College, the Phi Kappa Phi Honor Society, the Chemistry Honor Society, where I am serving as the current chapter president, and I have done internships with Dow Chemical Shore Program and Corning. I also have sponsorships with the National Science Foundation, FOSSI, and Science Co. So solving the world's issues with photocatalytic applications. The environment is worsening due to toxic materials being released into our environment, but more specifically, I would like to speak on the textile industries, which are releasing toxic materials into our waterways, which are not only harmful for our wildlife, but also for human consumption. The synthesis of these titanium oxynitride-based materials can assist with water splitting, removing waste from water, and other applications. Titanium oxynitride is also valuable due to its redox availability, low cost, non-toxicity, and high stability. TiO2 is a common catalyst used in photocatalytic activity, but has limitations due to the wide band gap for application in visible light. The addition of heteroatoms to TiO2 expands the possibilities of tuning properties such as band gap to enhance performance. The key to making sure that TiO2 works in visible light is by narrowing the band gap through a nitrogen source. So the aim of my research is to improve the photocatalytic activity of TiO2 while also creating a simple analysis method for the formation of titanium oxynitride. And the method I used was the evaporated induced self-assembly method, also known as the ISA method. So the materials I used were my F127 polymer, titanium isopropyl oxide, various grams of urea, which was my nitrogen source, and ethanol as my solvent. Those materials were then mixed, evaporated, which were co-assembled, and through polymerization left me with my mesoporous material, which was a white powder that was calcined at 800 degrees Celsius through a nitrogen condition and formed titanium oxynitride. And so some of the characterizations that I did were X-ray diffraction and scanning electron microscope. And with X-ray diffraction, I simply just compared my samples before and after calcination. And as you can see right here, these three major peaks show the crystallinity of my sample as well as the formation of the materials that I formed. As you can see, I did form titanium oxynitride. And with the scanning electron microscope, this just shows simply a visual of my sample before and after calcination. And so my results with band gap, in order to find band gap in the absorbance of light, I used DRS, which is diffuse reflectance spectroscopy. And so this showed a visual representation of, the significant decreasing in our band gap. As you can see, it did have significant decrease in both indirect light and direct light. And so I did photocatalytic testing with Congo red dye, which is heavily used in the textile industries. And that experimental setup consisted of a high power flashlight that represented the sun for a renewable energy source, my catalyst, which was added to a diluted concentration of the Congo red dye, and I monitored over time to check the degradation of the dye, as you can see both visually and through the graph. And in conclusion, I had a successful synthesis of titanium oxynitride using the ISA method. Characterizations revealed both the physical and chemical properties of titanium oxynitride, and a successful photocatalytic activity of visible light with 71% of the degradation of the dye degraded after 120 minutes. And if you would like to read more upon my research, this is my recent publication as of July 2024. And my next steps would be to investigate more applications with our titanium oxynitride sample, working on other compounds such as cerium dioxide, titanium dioxide, ruthenium dioxide, that's a lot, composite for hydrogen generation, and working on other publications for my full titanium oxynitride research findings. And just a little bit of Aggie pride, this is me with Astronaut Cook, the governor of North Carolina, Chancellor Martin, and other astronaut scholars. Any questions?
Wow. Good news here. Can we have one question? One question.
Hi, great presentation. I was
Thank you.
wondering if you know anything about nitrogen doping affecting conductivity of your sample and if that affects your results at all.
Yes, it does. I think it comes with the actual grams of urea. That is where the conductivity may play a role in.
All right. Thank you so much, Kennedy. All right. I made a public service announcement about squishing. I'm assuming everybody took a shower. So come on in. Those of you in the back, why don't you come in? Let's fill in, please. And then we're going to have one more speaker before we take a little bit of a break. But please come on in. I see some spots over here. And there are some definite spots right here in the front. So we welcome you in. Thank you for coming. All right, we have one more speaker before we take a little break for the morning. And it's Garrett Hanze. And I'm just going to go with characterizing the role because there's words that I can't see. So welcome, Garrett.
All right, good morning, everybody. Good morning, there we go. All right, it's really tense in here. All right, yes, my name is Garrett Hanze, and I study biochemistry at North Dakota State University. My research involves characterizing the role of coproheme decarboxylase, that enzyme right there, and it's in heme B biosynthesis. And that's heme B, an iron-containing coordination complex of a porphyrin ligand, which is the big ring. All right, now before I talk about my research, I need you guys to understand the importance of heme B as a cofactor. So you may recognize it for its role in oxygen transport, imparting the red color on your blood. But it's also in steroidogenesis, catalase reactions, electron transport, peroxidase reactions, sensing and signal transduction, blah, 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 and so many more. And that's just heme B, which is the precursor for other heme molecules. So essentially, heme B is important to almost every single organism on Earth. They would not survive without it. So let's talk about its biosynthesis, which starts from delta aminolevulinic acid and proceeds through several enzyme-catalyzed reactions to produce heme B. This is the canonical pathway in gram-negative bacteria and eukaryotes, including us. However, the pathway diverges in gram-positive bacteria. And such a divergence, some of you may recognize as a textbook case for targeted antimicrobial therapies, or antibiotics. But first, we have to understand how this pathway functions. And so my research involves the last enzyme of the pathway, coproheme decarboxylase, or CHDC. Now, CHDC takes coproheme 3 as its substrate, which will undergo 2 hydrogen peroxide-dependent oxidative decarboxylations. First at position 2, yielding the half product harderoheme, then at position 4, producing heme B. Now, one of my first objectives was to determine the amount of hydrogen peroxide necessary to convert coproheme to heme B. And what's really nice about all these molecules, let me go back for a second, they are really strong chromophores, super duper aromatic, so we can use optical absorbance spectrophotometry. And that's where I get these really pretty spectra. Now I'm gonna skip over the data analysis, but these intersections of these lines show that they show the total amount of hydrogen peroxide in equivalents needed for each decarboxylation. And this is consistent with the hypothesis that each decarboxylation takes 1 equivalent. Now, other research has shown that a specific mutant of CHDC stops after the first decarboxylation. This mutation would be CHDC K149A. And I did the same experiment and saw only a single intersection at 1 equivalent, which is consistent with a single decarboxylation. So let's talk about the active site. This is super exciting. Don't be overwhelmed. So coproheme is stabilized in the active site of CHDC with propionates 2, 4, and 6 forming ionic interactions with residues on the surface. Kind of like magnets. I know the physicists don't like that. And then there's also a catalytic tyrosine necessary for each decarboxylation. Our hypothesis is that mutating K149 removes this ionic interaction with propionate 4, therefore providing less stability for coproheme. So I tested these affinities, doing more titrations, and more titrations. I got dissociation constants abbreviated as KD. Now, the lower the KD, the stronger the affinity of the enzyme for the substrate. So I got KDs for CHDC with coproheme as well as heme B, and we can see that CHDC binds coproheme with a much stronger affinity than heme B. Repeating this with the mutation, I saw that the affinity for coproheme is much less than the wild-type enzyme, and it's just slightly weaker for heme B. Now, all of this data is consistent with the hypothesis I stated earlier. Removing this ionic interaction decreases the stability. But after the first decarboxylation, propionate 4 must turn in the active site so that it can interact with this catalytic tyrosine. And the mutation likely stops because that turn is no longer driven by this ionic interaction with propionate 6, which is really neat. So let's wrap it up. The affinity of CHDC for copraheme is much greater than it is for heme B. Lysine 149 helps stabilize copraheme in the active site of CHDC. And without that residue, the second decarboxylation does not occur, leading to the hypothesis that it's necessary for the reorientation of harderoheme. My future research includes measuring the rate of the mutant reaction to compare with that of the wild type, which is really cool, like I said, because only the first decarboxylation occurs. We can isolate just that, characterize just the first decarboxylation. And then we want to measure reaction rates and the thermodynamic driving force of copraheme transfer from the previous enzyme in the pathway, CPFC, to CHDC, as well as my mutant. Lastly, I'd like to acknowledge our funding sources, my professors, our PhD candidate, and other undergraduate researchers for helping me with my research, and also the Astronaut Scholarship Foundation. Thank you.
Yay. Thank you, Garrett. Let's take one question for Garrett. No one has a question?
Oh, there's a question.
Oh, there's a question. Here we are. We're racing with the microphones.
Hi, Garrett. I'm a chemist, and I actually understood your biochemistry for the first time, so thank you so much.
Good. I'm glad. I really tried.
It was great. Super interested in what kind of prokaryotes you're interested in targeting with this therapy. Is this a universal reaction that is typical just of prokaryotes? Or?
Yeah. So let me go back pretty far. I have a lot of animations. I really love this slide back here. So let's see. Why isn't it highlighted? There we go. Okay, so this is the pathway in gram-negative bacteria and eukaryotes. So this is what almost every organism uses. It was discovered about 10 years ago that gram-positive bacteria have a different pathway. I should have said this. Gram-positive bacteria like Staphylococcus aureus or MRSA. So the goal is to characterize this pathway so someday some other smart people can come up with antibiotics for something like MRSA. Yeah. Does that answer your question?
Yeah, that's great. Thank you.
Great. Thank you, Garrett, very much. All right, so we need a promise from you. Otherwise, Justine will get mad at me. We are actually going to give a good 5-6 minutes, but then out of the room, but then you come back and be here in let's go 6 minutes. Run. Thank you. Hello, everybody. It has been 6 minutes at least. Take a seat, please. I refuse to whistle because I can't. There we go. Thank you. Welcome back. Welcome back to part 2 of today's technical conference. There are 3 parts, in case you wanted to know. Actually, there's 27 parts. Oh, wait, we'll be here till 5. All right, welcome back. For those of you who have joined us, there's lots of seats. We really appreciate everybody squeezing in so that everybody has a nice place to sit and relax and hear what's next. Okay, so we've taken our break, maybe a little bit longer than we should have, but this was anticipated in our timing. So now, we are going to start with Zachary Abrams, and he and I talked a little bit about this. This is super cool, so I'm excited for the treatment of mental health disorders. Thank you, Zachary.
My name is Zachary Abrams. I'm a student at Miami University, the one in Ohio. I know there's been some confusion with that. And I'm trying to create a new treatment for something that you or a loved one might be dealing with right now, and that is mental health conditions. So my lab produces a few hallucinogenic compounds, one of which is DMT, which has shown the ability to help individuals with treatment-resistant mental health conditions. And this is the very basis for my lab's interest in these compounds. We seek to make it in a more economical way to eventually make it more accessible for individuals in need in the future. The way that we actually produce it is using metabolic engineering techniques, which is a way of taking DNA from nature and inputting it into our lab's E. coli cells. And a few organisms whose DNA we actually pull to make these compounds include mushrooms, toads, and get this, even humans. So what we're trying to do in my lab right now is create DMT derivatives, or in other words, we're trying to slightly change the chemical structure of DMT to identify a compound that interacts with our brain in such a way that does not elicit a hallucination, but still maintains this therapeutic benefit of standard DMT. So you might be asking, why are we trying to do this? Well, the hallucinogenic characteristic of DMT creates certain challenges, one of which is it makes the drug classified as Schedule 1 by the DEA. This means that DMT is considered to have a high potential for abuse, and it's not considered to have any medical value. Both these things regarding DMT are not true. Another point is that it's really hard to blind participants in clinical trials because when someone has DMT, they're going to know that they're taking it because they're going to have a hallucination. So a question, well, while we've been investigating these DMT derivatives, we've been asking, is this hallucination actually required to have the therapeutic benefit? And we would like to think not only for simplicity and convenience, but also because of some initial investigation we've done with another psychedelic compound, psilocybin. Its derivative, called norbaeocystin, has shown to have these desired characteristics of having a therapeutic benefit without a hallucination. And this is super cool, but we've not done or looked as in depth with DMT. And this is kind of where my work comes in. So originally, we'd produce DMT in our lab by first supplementing our cells with indole. Indole is then processed by the enzyme TRPB, which is natively found in E. coli cells to form tryptophan. And I'm sure you've all heard of this compound because this is what fills your stomach and your body after you've had a lot of turkey on Thanksgiving. And then tryptophan is then acted on by PSID, which is an enzyme natively found in mushrooms. And it must be noted that my lab has actually input this enzyme into the E. coli cells in order to remove a carboxyl group, or CO2, from tryptophan to form tryptamine. Tryptamine is then acted on by the enzyme INMT, which is a methyltransferase that is natively found in humans. And again, this is another enzyme that my lab has input into the E. coli cells to add a methyl group onto tryptamine to form N-methyltryptamine. This N-methyltryptamine is then acted on by the INMT enzyme one more time to form DMT. And so what I've done is I've replaced this INMT enzyme with one that performs the exact same function, but from the toad species Rhinella marina. And what this has allowed us to do is not only have high DMT production, but we're also capable of the RMNT enzyme is also capable of accepting a range of substrates. And so what I mean by that is that we can actually give the RMNT enzyme compounds that have variety not only in their functional group, but also their functional group's respective position to generate alternative or DMT derivative final compounds. And with this, we've actually been able to generate 23 new DMT derivative final products. And so how do we do this? It's actually super simple. All we do is we change the compound that we start with. So let's say instead of supplementing indole, we supplement 6-fluoroindole. All these alternative compounds are able to be processed by the respective enzymes within the pathway, and we end up with 6-fluoro-DMT. And this is one of the 23 new derivatives that we're capable of producing. So great, we have these 23 new derivatives, but what do we do next? Well, my lab is only involved in the synthesis of these compounds. And so we need to pass them on to our collaborators who will go ahead and test them on rats for the desired traits of not having a hallucination, but still maintaining this therapeutic benefit. Once we've hopefully identified this golden compound, my lab will take back over and we'll try and produce it on a larger scale and then identify ways to purify it. Before I conclude, I want to emphasize that I truly believe that these drugs have the potential to revolutionize how we treat mental health conditions, not only here on Earth, but maybe even in the future in space. I want to thank the Jones Lab, especially my PI, Dr. Jones, for all of his support, and also my mentor, Jessica Flower, and of course, the Astronaut Scholarship Foundation. Thank you.
There might be a few questions here.
Fascinating research. Can you elaborate a little bit more on the actual therapeutic benefit for someone with PTSD? What does it actually do to the brain, or what does it mitigate from a certain illness of that nature?
Yeah, so that's still something that we're kind of trying to uncover, and that's what our collaborators' lab is working on. That's actually testing the compound. And yeah, we don't entirely know how that works, so we're looking into that.
One more question.
Hi, great talk. You mentioned that
obviously your collaborators do the tests in rats. I was just wondering how you can tell whether they're having hallucinations.
Totally. So to monitor for the hallucination, what we do is we surgically implant a magnet on top of the rat's head, and then we administer the drug, and then basically we look at the rats for a certain type of head twitch, and that will tell us if a hallucination is happening or not. And then just to go on, we monitor the therapeutic benefit by literally dropping the rats in a bucket of water, and then we just measure their propensity to be resilient when facing the stressor of water. And so essentially the longer that they're able to swim, the greater the therapeutic benefit of the drug. And of course, we don't let the rats drown, we take them out of the water after they stop swimming.
I was concerned. So great, thank you, Zach, excellent. Next, let's welcome Susan Harris on Extended Structure Activity Relationship Studies. Welcome, Susan.
All right. Hi, everyone. My name is Lainey Harris. I'm a student at the University of Colorado Boulder in the Wong Lab, and today I'm going to be talking about structure-activity relationship studies of novel resistance-modifying agents for colistin. So essentially, my project involves developing compounds to combat antimicrobial resistance by extending the clinical efficacy of colistin, which is a last resort antibiotic. So most of you have probably heard of the challenge of antimicrobial resistance, but it has the potential to become a greater global health crisis in the next few decades than many people realize. In 2019, an estimated 1.27 million deaths were directly attributable to AMR, but by 2050, that number is expected to exceed 10 million, which rivals current cancer death rates worldwide. So the bacteria of highest concern are known as the escape pathogens, and they are frequently multi-drug resistant, and they often cause severe nosocomial infections, resulting in high morbidity and mortality. They can be divided into gram-positive and gram-negative organisms, with the majority being gram-negative. So my project focuses on colistin, which is a last resort antibiotic for the treatment of multi-drug resistant gram-negative bacterial infections. And by last resort, I mean that if your doctor prescribes you colistin, it means there are no other antibiotics that could effectively treat your infection, which is very bad. So up until 2015, only chromosomal forms of colistin resistance had been identified, but the discovery of mobilized colistin resistance genes introduced the potential for horizontal gene transfer, which has resulted in more rapidly spreading resistance. So resistance-modifying agents are non-antibiotic compounds that resensitize resistant bacteria to existing antibiotics. And some examples you may be familiar with of RMA antibiotic combinations are piperacillin tazobactam and augmentin, which is amoxicillin and clavulanic acid. And these are both penicillins paired with beta-lactamase inhibitors, which are currently the only clinically approved form of resistance-modifying agent. And the advantages of resistance-modifying agents over traditional antibiotic development are there's a greater number of undiscovered targets because of the relative infancy of the approach, and additionally, there's lower resistance potential because they typically target non-essential genes and gene products. So my lab used a high-throughput screening approach to discover RMA number 1, which has high colistin potentiating activity in a variety of bacterial strains, and subsequent structure-activity relationship studies involving similar compounds containing 1,2,5-oxadiazolo-3,4-B-pyrazine, or ODP, resulted in the discovery of an even more potent and selective analog, which is RMA number 2. So we are currently working on a second round of structure-activity relationship studies, and to date we have synthesized over 100 compounds within this class of RMAs. And for any chemists out there, this is an example of the synthesis, but I'm not going to go into detail right now. So for biological testing, we evaluated the activity and toxicity of our RMAs using minimum inhibitory concentrations, minimum resensitizing concentrations, and GI50s. Minimum inhibitory and minimum resensitizing concentrations are measures of activity that we determined through broth microdilution assays, and then the GI50s are measures of toxicity that we determined through cell viability assays using human hepatocellular carcinoma cells. So the most promising compound that we discovered through these structure-activity relationship studies is actually one that I synthesized, 8G, and it had the best ratio of activity to toxicity. And then it also was able to reduce the minimum inhibitory concentration of colistin to below the clinical breakpoint in 7 bacterial strains, including 3 of the escape pathogens. So one of the biggest unanswered questions we have with this project is how our compounds work. So I'm going to be starting mechanistic studies soon to try to figure that out. We are also going to send our best compounds to a different lab for in vivo pharmacokinetic and pharmacodynamic studies. And hopefully after that, they'll move on to clinical trials. So I would like to thank all the members of the Wong Lab that contributed to this project, as well as the Department of Chemistry and the Undergraduate Research Opportunities Program at CU Boulder for the funding. And then thank you to Club for the Future for funding my astronaut scholarship. And of course, thank you to ASF for bringing us all here today. I can take questions.
Thank you very much. Such important research as with you all. Questions, please.
Hi, great talk. Did you use any computational methods to determine like what point you towards like compounds to synthesize, and are you planning on using any to like predict the like ligand binding or anything in those like in the metabolic stuff?
Yeah, so we didn't. The way we decided like what analogs to synthesize, at first it was based off of a previous paper that was published on this class of compounds, actually describing them as mitochondrial uncouplers. And so we synthesized some of those compounds because we thought that the protonophore activity might be linked to the like activity as RMAs. And then after that, we just sort of made small modifications of those compounds and looked at what happened and yeah, just continued from there.
All right, thank you so much. Thank you. All right, next, let's please welcome Justin Vin, interrogating the cellular impact of sonodynamic therapy on glioma cells. Justin, you're up. And look at how sharp he is dressed.
Good morning, everyone. My name is Justin Vin, and I'm a fourth-year student at the University of Virginia. Today, I want to talk to you about interrogating the cellular impact of sonodynamic therapy on glioma cells. So, let's up the stakes. Glioblastoma is a highly aggressive and deadly type of brain cancer. In America, it's also the most prevalent form of brain cancer. And despite our best treatment modalities currently, fewer than 6% of patients will survive beyond 5 years. This is bad. It is very difficult to remove. With surgery, you're operating within a very difficult brain space. It's hard to remove the tumor completely, and with traditional chemotherapy and radiotherapy, there's also a lot of off-target effects. And it has a high recurrence rate because the tumor is aggressive and will often develop resistance to these treatment methods. And so the field is ripe for novel methods of treating glioblastoma. Today I want to talk to you about one such method, sonodynamic therapy. It uses sound and has 2 components. The first part is 5-aminolevulinic acid. Mouthful. I'm going to call it 5-AOA. The important thing to remember about this is that it's non-cytotoxic. By itself, doesn't really do anything. Doesn't kill cells, doesn't really do anything with cancer. And over the past 10 years, it's been used as a surgical aid in treating glioblastoma. It fluoresces under certain wavelengths and allows surgeons to more easily see the tumors that they want to resect. The other part of this treatment method is focused ultrasound. We can take high-intensity sound waves and focus them to a small point. Using sound has several advantages. The first part is that it's also non-cytotoxic. And the regime that we're using it in also doesn't really do anything. But because we're using sound, it's non-invasive. We can send these sound waves through the cranium, which removes the need for surgery, and it's non-ionizing, which is advantageous over radiation therapy. So remember, both these by themselves don't do anything. Combine them, though, and we get a new treatment modality, sonodynamic therapy. It is selectively cytotoxic for the tumors. And importantly, it's in current clinical trials at several institutions, including my home school of UVA. So, this is how it works. We take 5-AOA and administer it to patients, or in my case, cell cultures. And both normal cells and glioma cells will uptake 5-AOA and convert to protoporphyrin 9. And if that molecule looks familiar, it's because it's a precursor to heme, which Garrett very helpfully told us about a few minutes ago. Thanks, Garrett. Most cells will contain an enzyme called ferrochelatase that will convert it into heme. Tumor cells, however, have decreased activity of ferrochelatase, and a protoporphyrin 9 will therefore accumulate. We can take advantage of this. We can sonicate cells with a high accumulation with FUS, and in doing so, induce the production of reactive oxygen species. These are highly destructive and will lead to apoptosis, necrosis, in other words, cell death. This is a good thing if we're treating cancer. So my goal of my study, though, is to characterize the effects that it has on the tumor and the surrounding environment, and to optimize the therapy. Because if we can understand what happens on a cellular or molecular level, we can improve treatment for patients. And so there are several goals in my project. The first two that I do want to talk to you about are optimizing the parameters and characterizing cell death. So the relevant parameters here are looking at the dosing of 508 that we administer, how long do we incubate and allow the dose to stay with the cells, and as well as how much power do we sonicate them with and for how long. So let's look at cell culture parameters first. We found, after several experiments, that the most optimal parameter was using a 1 millimolar dose with a 4-hour incubation period. Using these parameters, we then went back and looked at the sonication parameters. And we found that there was a relationship between higher sonication power, higher durations. Either of those will lead to greater rates of cell death, which you can see with the purple bars. And of note, if you look to the right and look at the graphs here, you will see that temperature rise doesn't exceed 2 degrees Celsius for the lower power settings or 4 degrees Celsius for the higher power settings. This is good because it means that it's the combination therapy that's eliciting these effects, and it's not just us getting too excited and frying the cells with sound. And so moving forward, I want to continue optimizing these parameters for glioma cells. And I'm going to take these optimized parameters, then move them to 3D cultures, which are more representative of the human brain. And we have already started doing that, looking at G28 cell lines. I'm seeing a very similar dosing and incubation features. And finally, I want to investigate the secretome and extracellular vesicles to understand truly how this therapy affects the tumor and the surrounding space. And with that, I want to thank you for your time, for the Astronaut Scholarship Foundation for allowing me to present here today. And special gratitude goes to my advisor, Dr. Natasha Shabani, and of course, my wider university colleagues and my sponsors. Thank you.
Thank you, Justin. We have time for one question, please. One.
Oh, thank you for that. That was fantastic. What you're doing is like great work, seriously.
Thank you.
What motivated you to, move into this direction? This is fantastic.
I think focused ultrasound is what really motivated me to come here because it's just so different from the current treatment methods. It's less destructive than something like surgery or radiation therapy, and it has so many potential either on its own or in combination, like what we were seeing here. And so I think moving forward, precision cancer therapies are really what we need to move towards to give patients better outcomes with fewer side effects.
Thank you. Super cool.
Thank you.
Thank you, Justin. Next, let's welcome Anna Marie Thompson, Impact of LSD1 Inhibition on Gene Expression in Normal Neural Cells. Welcome, Anna Marie.
Good morning, everyone. My name is Anna Marie Thompson, and this summer I had the privilege of conducting research at the University of Texas MD Anderson Cancer Center, where I studied the impact of lysine-specific demethylase 1 inhibition on gene expression in normal neural cells. I'd like to begin by providing a little bit of background on lysine-specific demethylase 1, which I will refer to as LSD1. LSD1 is a histone-modifying enzyme that is an important epigenetic regulator in various cell types, specifically in stem cells, where it epigenetically regulates growth and differentiation. LSD1 is particularly significant in my field because it was the first lysine-specific demethylase to be discovered. Since its discovery, it has been associated with poor prognosis when dysregulated in certain neural cancers, such as glioblastoma, which we just heard about, and diffuse intrinsic pontine glioma, which is a type of incurable pediatric brain tumor. Pharmacological inhibition of LSD1 has been achieved using drug repurposing. Previously, drugs were on the market targeting LSD1 for the treatment of neurological disorders such as Alzheimer's and depression. So since these drugs were known to be safe and effective, they were able to be repurposed to specifically target LSD1 in cancer cells. Some of these LSD1 inhibitors have been shown to cross the blood-brain barrier, and many of them have been tested in clinical trials for various malignancies, but not much work has been done to this point testing them in neural cancers. Previously, the Chandra lab at MD Anderson did a gene expression analysis in normal human astrocytes, which are representative of healthy neural cells, and LN18 cells, which that is an adult glioblastoma cell line. They found a set of 37 genes specifically upregulated in the NHAs, which were resistant to LSD1 inhibition, but not in the LN18 cells, which were sensitive to LSD1 inhibition. When they probed that gene set, they found 5 specific genes that have known roles in other cancer types. And this is important preliminary work because the long-term goal would be treating cancers like DIPG, diffuse intrinsic pontine glioma, using LSD1 inhibitors while sparing the health of normal neural cells, which is particularly important in young pediatric patients. So my work this summer specifically wanted to determine what would happen in these normal human astrocytes, these healthy neural cells, when we continuously exposed them to LSD1 inhibition. To do that, I worked with a patient-derived NHA cell line, which I cultured in T25 flasks. The cells were required to be passaged every 3 to 4 days, at which times I would treat them with either DMSO, which served as my control treatment, or 10 micromolars of a clinically relevant LSD1 inhibitor. At days 7 and 12, I also harvested my remaining cells during the passage to isolate RNA and run RT-qPCR to analyze gene expression levels. Also, at each time point, beginning at day 0, I measured the viability of both treatment groups. What I found was that NHA are capable of tolerating low doses of LSD1 inhibitors over time. As you can see here, both of my treatment groups maintained high viabilities throughout the entire duration of my experiment, and there was very little difference in viability between the 2 treatment groups. It's important to note that viability remains above 90% throughout the entire 2-week treatment period. I also found that continuous exposure to a clinically relevant LSD1 inhibitor results in upregulation of genes associated with resistance to LSD1 inhibition. As you can see here, following 1 week of treatment, 4 of the 5 genes of interest were significantly upregulated in the NHAs. That pattern continued after 2 weeks of treatment, and the same 4 genes became even more significantly upregulated. And this is important because these genes could be associated with neural cell survival in these normal human astrocytes. In the future, I would like to determine if intergenic dependencies exist in expression levels of these genes of interest by knocking out a single gene and determining the effect that that has on the remaining genes that are intact. I'm also interested in patterns of resistance gene expression in transformed cancer cells, and I would like to compare and contrast those expression patterns with those that I saw this summer in the normal human astrocytes. Lastly, I would like to thank all the members of the Chandra lab at MD Anderson, specifically Dr. Joya Chandra, my PI, and Do Kwal Nam, my lab mentor. I would also like to thank the Summer Program in Cancer Research and the National Cancer Institute for funding this work, as well as Mississippi State University and the Astronaut Scholarship Foundation for the opportunity to present today. Thank you very much, and I welcome questions.
Thank you so much. All right, let's take one question, please. Who's got the question?
Beautiful talk. I wanted to ask, since you use normal human astrocytes, have you thought about using like microglia instead?
That is not something that our lab has previously done. I think that could be a really interesting future direction to also look at the, off-target effects of these drugs on the non-cancer cells. So that's not any work that I can speak to at this point, but I think that's a great idea for future work. So thank you for that.
Thank you.
Thank you so much. Thank you. All right. Next, we'd like to welcome David Heeson on joint tensorial and convolutionary neural network methods for image deblurring and denoising. And when you're done, help me denoise my job. Welcome,
I will try.
David.
Thank you very much. Okay. Okay. Thank you very much. My name is David Hassan. I'm a student at Mississippi State University. This is a project I started recently with Dr. Navaska from UAB. Her and her collaborators basically created a tensorial method, which means it's analytical, no machine learning. You just have a bunch of matrices and pass an image to them, and you get a denoised image. And I'm basically working on making a machine learning extension to that with the hope to make an open source pipeline which can denoise and deblur images using both analytical and machine learning methods in tandem for multiple reasons. First of all, this would limit the amount of learning data we need to fit into a machine learning model because you basically have an image in a chaotic state. And then our analytical method can basically address the chaos within the image, denoise it a bit, which will make the machine learning model have to be less powerful. And by that, it reduces training time. It's going to reduce the amount of computational needs you're going to have by reducing time and space complexity. And will also show the use of analytical methods even in an age where machine learning is kind of the big thing. So to move on, I'll be covering the analytical method, then I'll also do a brief overview on my sketch work on the machine learning method, and then the future work, which is really the meat of this, where we're going to try to create this pipeline, potentially in Python or with Rust. So to move on with some mathematics, basically we're going to use the ROF model to minimize the noise in our image. This is basically a method in which we can try to retrieve a correct image by minimizing the variation within the noisy image. And this is a very effective method we're choosing because it favors edge detection by basically creating piecewise functions out of this minimization. So this way, by adjusting that lambda parameter, we can basically turn the analytical algorithm where to pick out an edge and where to not pick out an edge. Like how sensitive can it be to variation? So at very high variation intervals, it's going to be like, oh, that's an edge, so we can keep those edges. And the actual workhorse of this is the FIST algorithm, which is basically a way to make this more computationally efficient. I will not spend too much time explaining it, but it's once again just a minimization problem, which allows us to create a linear transfer from the tensors. And very important thing to note, something very unique about our analytical approach is that it can also denoise in the color space. So it's not only a plain edge denoising, but we can also access three-dimensional and four-dimensional tensors to denoise both color images and color videos. And to talk a bit about the actual analytical results, this is pure analytical, so just the straight tensor method. And you can see as we're adjusting that lambda parameter, we can achieve optimal big signal to noise ratio, which is just a very common approach to quantify how denoised an image is. And something interesting, you can see that as we increase lambda way too much, we can actually worsen image quality. So this is a parameter we have to very carefully adjust. And this is actually something else we'll potentially use machine learning for to learn what's the best way to adjust this parameter. And if you also look at the image clearly, even at the lambda 20, you can see there's something weird happening in the color space. Like the purple is becoming just obvious, but the edges are becoming sharper as compared to the input hazed image. Why hazing images just by applying a Gaussian random filter, nothing fancy. So what would be interesting is to try to explore a machine learning method that can help correct this correlation basically, but also remain a very lightweight model. So I've worked with the Shallow Unit model by Naik, Starnaka, and Mital, and as you can see, it's a very small model. I was able to run it on my laptop, which is a 2017 ThinkPad, so you don't need very high computational efficiency. I've also used a pre-trained model, and it's made specifically for underwater imaging. And this was basically some of the sketch work I've done. And something really interesting with this is that, so ML is just machine learning, and then deep blur is just our output. Our analytical method actually managed to achieve better results, very slightly better results than the just machine learning model trained for this very specific data set. So here is basically the input images. This is the haze image from their data set. We applied the Gaussian filter just in case it made a difference, and this is the true image. So here I have the outputs you can see, but an interesting one here, but these are the tandem combination, and you can see a bit of change in the color, but again, this is without any training on our own. This is just by passing into the trained model. So to quickly go into future work, I'm sorry. So basically, we want to try to now create our own machine learning model to work in tandem and be trained with this analytical method in mind. Also using machine learning to adjust this lambda parameter and just try to get an overall pipeline for this. And thank you to the Astronaut Foundation for having me here and Mississippi State University for mentoring me to this point. Questions?
Thank you, David. All right, we have time for one question. Go ahead. Oh, there we go. Super easy. No racing.
Hi, David. Great talk. It's so interesting to see how there are still analytical methods being explored in a time where numerical methods are dominating all of science. So my question for you is, how easy would it be for one to implement the analytical method without any mathematical training?
I mean, we have already created and coded a mathematical method in MathCrab, so you could really just, if you know that the code is created, you really just have to take the code and adjust lambda as needed to make the image good. So it really takes absolutely no expertise even in coding. It's just press play, basically.
All right. Thank you, David.
Thank you.
Next, we have Elisa Williams, and I'm going to just leave it at, I knew it!
Hello, everyone. My name is Alyssa Williams. You can just call me Allie. I'm from Mississippi State University, and I study learning and memory, which is important because we all use it, hopefully. So specifically, what my lab at the University of Washington was interested in was capturing individual differences in memory ability. So one way that we do this is by using computational modeling, and what that might look like is doing something like an adaptive factoring learning task. So here we're giving the participant two different stimuli that we ask them to encode together. So maybe like a flag and its respective country name. And then over time, we predict the exact amount of time it's going to take them to forget that fact. So at that point in time, we ask them again, and depending on their response, we'll update our predictions. So we do this again and again until we get the overall speed of forgetting parameter, which is very stable and reliable, and has also been correlated with resting state functional connectivity. And just moving forward, you want to remember things for longer, so a lower speed of forgetting score is actually better. And this is complicated, and I don't have time to explain it, but basically this is taking into account things like the testing effect, recency effect, power law of forgetting, all to get this one speed of forgetting parameter. So my question was, how is prior knowledge currently affecting these assessments? So what if you already knew the Aruba flag because you went on vacation there last week? So is there a way that we can computationally identify and resolve this confound in our model? So to do this, I collected data from 70 UW undergraduates, and they first did a prior knowledge survey. So they saw something like this, where they had to recall like maybe the Bangladesh flag from memory, and if they got it right on the very first trial, it was marked as them having prior knowledge. Then we gave them incorrect and correct feedback, and they completed the rest of the adaptive fact learning task afterwards, where they learned about 30 flags, some that they probably did know, some that they probably didn't, so we could capture that variation in our model. And then we did the new part, which is trial by trial maximum likelihoods to recover base level activations. What does that mean? So basically we took our original model and we added one new letter. And what this did was using just accuracy and response time, so the initial behavioral data that we had already been collecting, we were able to retroactively estimate this idea of activation, where if like you're very, very first trying to think of Bangladesh, how active is that in your mind? What is your likelihood that you're going to be able to retrieve that? So that's what we're capturing here. And the idea is if you're answering these questions super fast, you're getting them right, the model is thinking that you're learning better than you actually are. So if you just had prior knowledge, it's going to give you an inaccurately low estimate of speed of forgetting. And so when we separate this across participants, we see that, yes, this is indeed a confound in our model. And next, we wanted to see if we can dissociate that by using the maximum likelihood. So these are the values that we get. So we can see at the all the way on the left, that's what we're predicting as having prior knowledge because it has a high recovered base level activation. Hopefully you can see this aligns with what you would think people would know. So Japan, India, South Korea, China, and Jamaica, and this also aligns with our ground truth data. So what we can see here is an overall kind of like inflated effect, and that's what I like to call the I knew it effect. So when you actually have you're trying to think of a fact and somebody just tells you the answer and you're like, oh yeah, I knew that. So that's kind of what we're seeing here with this base level activation. And then to try to predict which facts people actually knew beforehand without actually knowing that, we got that right about 81% of the time, which is pretty cool. And then on average, we showed that with a linear mixed effects model that this was getting just the trend right. So this is great, but why do we care? So what is cool about this is the original algorithm is actually used, my University of Washington lab used it to make a company that outsources to schools. So about 700,000 kids across the world currently use this to learn vocab in a very efficient way. And what we wanted to do was use this to diagnose early onset Alzheimer's. So if you guys know anybody, the thing that people struggle with cognitive impairment is taking new facts and converting that into long-term memory, which is exactly what people are doing in this task. And we actually see that in a single 8-minute task, we can get about 93% accuracy, which is actually just as good as the clinical gold standard. So what's cool about this is that it's very accessible and it's actually repeatable because you can use any different facts. So once we correct for hopefully this prior knowledge confound, we can make this even more accurate. So with that, I would like to thank my lab, the Astronaut Scholarship Foundation, and all of you guys for listening. Thank you.
Yeah, thank you, Allie. I'm sorry. Yes. Thank you, Allie. And we were here what? No, sorry, okay, go ahead. Who's got the question? Did you see what I did there? Or not? Question. There's got to be at least one.
So, you were mentioning about correcting for the prior knowledge confound. How would that actually look in your future research?
Yeah, so that's our current next direction. So actually correcting for this prior knowledge is kind of difficult, but what's cool about this is that it can be applied retroactively to the task and using the exact same data that we've already collected from the task. So we have like longitudinal studies for like a year where people collected data every single week, measuring the speed of forgetting, and we are actually planning to retroactively apply that to all of that data to see if we can like optimize a model to best correct for the prior knowledge. Thank you.
Thank you so much, Allie. Fascinating research. We would next like to welcome Vikas Patel, and I'll just leave yours at space is hard.
So thank you all very much. My name is Vikas Patel, and my job here is to convince you that space is hard, because NASA and many of these companies make it look way too easy. So the Space Technologies Lab at Embry-Riddle has been given the chance to create a few space payloads, the first one being on the Blue Origin New Shepard 23 launch. That was in September of 2022, which, as some of you may remember, had an anomaly. So due to the booster failure, the capsule had to be jettisoned away. And fortunately, we were able to refly about a year and 3 months later on New Shepard 24. But in that process, Blue Origin had to go through a very rigorous recertification process, which was a fantastic learning opportunity for everyone as a part of the team. Now, the payload that was on the mission was a demonstration of EagleCam. EagleCam was on the Intuitive Machines lander that went to the moon in February of 2024. The idea of EagleCam is that as the lunar lander came down, at 30 meters above the surface, EagleCam would deploy and continuously take pictures to not only be the first student payload on the moon, but record the first third-person view of a lunar landing. However, as many of us know, the Intuitive Machines lander did not land successfully. Due to the hard landing, there was a lot of communication errors, and that was due to the fact that a laser altimeter was not working. We noticed that in orbit, and we decided to wait until we were on the ground safely to deploy. After we realized that the communication issue was going on, we knew we had to select 1 to 2 images to bring back because we couldn't bring back all of our data. And so we went through a lot of testing and simulation there on the right, based on the sun position and where we were, to basically determine what the best exposure setting would be to bring back. And unfortunately, as we went to go and try to deploy it, we realized that the hard and fast landing resulted in the inoperation of a lot of our hardware, which resulted in limited data. Some people may say that, from our flight history, we're bad luck to carry on board, but as a man of science with 2 data points, that's not enough to draw a conclusion. And so a lot of that learning has gone into creating our next payload called LLAMAs, which stands for Literally Looking at More Astronauts in Space. And so it's mounted inside the Dragon capsule on the upcoming Polaris Dawn mission. The idea is that these private astronauts will turn us on before they do their spacewalk, and we get to record the first commercial spacewalk using 2 lenses about eye width apart, each with 186 degrees field of view. And we can then take that video back and turn it into a VR experience with 3D depth. Now, one of the main issues that I had to deal with as I was working on this project was the thermals. So it turns out computers are these really annoying things that convert electrical energy into heat, and that heat has to go somewhere. And so when you're doing an EVA, the entire atmosphere is evacuated, and so the only way to expel that heat is through radiation and conduction. And as some of you know, the radiation and conduction heat transfer methods are highly dependent on the surrounding temperatures. Since the Dragon capsule has never been sent up in orbit in this way to do an EVA, there's a lot of uncertainty on how hot the inside of the capsule will get, which directly has a result on how long we'll be able to record for. That heat dissipation correlates to how long it takes for us to get up to our cutoff temperature due to astronaut safety. And despite all of the thermal modeling and simulation that we can do, there's only one way to find out how it does, and that's to launch it. Fortunately, here in 9 days, Polaris Dawn is scheduled to launch on August 26th, early in the morning. And in the subsequent few days, we'll get the spacewalk, and we'll see how it does. And with that, I want to thank you all for listening, thank the Astronaut Scholarship Foundation for the opportunity to present, and thank the Space Technologies Lab for the chance to work on such an innovative project.
Fantastic. Thank you, Vikas. Let's have a question for Vikas.
Great talk. So for, by the way, llamas, whoever thought of that name needs a pay raise.
You have to have fun in aerospace.
Is it meant to be carried by the astronaut, or will it be mounted on Dragon?
No, so it's mounted inside the capsule. So there on the right, there's normally a mobility aid, and so that mobility aid gets taken out and replaced by us. And then back here on the bottom, that mobility aid is put onto the bottom of here so that the astronauts can still use something to hold onto and move around.
Gotcha. Thank you.
Of course.
Thank you so much. Let's not send llamas into space quite yet, but that's fascinating. Thank you. All right. Buongiorno, Luca. Luca Valente is going to talk about Buongiorno, Signor. Dynamics of an aircraft while carrying mass and inertial properties. Welcome, Luca. Ciao.
Ciao. I'm Luca Valenti from the United States Air Force Academy, and I'd like to talk to you about the dynamics of an aircraft with varying mass and inertial properties. So let's talk about payload conveyance for a second. If we think about small UAVs, payload conveyance, we usually think about rotorcraft, and the reason for that is that delivery systems like Amazon or other companies think that that is an effective way to deliver a payload in a highly urbanized area where you need to maneuver and you need to place the payload gently. And it is also an effective way because the center of gravity of the payload can always be under the aircraft. But there are some disadvantages to rotorcraft UAVs, and that's in terms of thrust-to-weight ratio. They require a thrust-to-weight ratio greater than 1, and they don't go super fast, and they have issues in terms of autonomy and therefore range. So we were interested in exploring solutions for payload delivery of UAVs for systems other than rotorcraft, but they present their own challenges as well. While they do promise a greater range and a greater speed, they have payload limitations in terms of envelope of the CG placement, therefore payload positioning and payload mass that you can actually carry. But we're interested in expanding that payload envelope because we think it's possible, and the inspiration for that comes from nature. So here's an example of a bird carrying a very large prey where the center of gravity is arguably behind the aerodynamic center of the wing. And that's something that in flight mechanics we don't want because it induces a pitch-up tendency which is statically unstable. And that's something that you have to correct for, and the correction energy that you would need would require you to decrease the autonomy essentially. So you don't want to do that. But birds have figured it out. This bird is gliding and the control surfaces are deflected, and yet they're not moving drastically once they're set in place. And if you didn't think that that was a negative static margin, look at this one. Carrying a full-size mountain goat, this is an eagle. See the deflection right there, but at the same time, it is a pretty stable gliding flight. So we think it's possible. I think it's worth investigating these parameters and investigating how a UAV model with fixed-wing aircraft would do with a payload all the way in the back. So I created a simple model with a wing and a tail connected by a massless rod, and I gave it inertial properties based on prior research. I then gave it a center of gravity and a center of gravity for the payload, and then I did a weighted average to find the overall center of gravity of the system. Once I have done that, I did a body-fixed wing system, and I decomposed lift and drag into the cardinal direction of the fixed body axis system. Then I calculated the dynamic characteristics of the system with the dynamics matrix, and what I found is, I think, very interesting. So here's the results from the real parts of the eigenvalues of the stability matrix, and these are the imaginary parts. Now, the real parts are associated with the actual instability in pitch, because we're looking at longitudinal stability at the moment. And you see over here that if you want a stable aircraft, you want a negative real part of the eigenvalue right here. If it crosses this zero axis, then it's going to be unstable. Now, this is for different payload masses that range from 10% of the body mass all the way to this black line, which is 100% of the body mass. And if you look right here, the green line is 80% body mass, and the black dotted line is 100% body mass. And you see that at some point, as you bring the payload back from the front, 0, all the way to the back, which is 1, they both are unstable. But quantitatively, the 100% is less unstable as you bring it back than an 80% payload, which means that perhaps if you do increase the payload and you place it wisely, you might not incur into a prohibitive energy cost correction in terms of active controls that you would need to correct the instability. This just validates our model, showing that the imaginary part associated with the oscillations of the system decreases as you increase the mass, and that's a property of inertia that makes it less likely to oscillate. So given that, we applied optimal control to the system to see what it would do with an infinite time horizon solution. And essentially what it does is it will bring the aircraft back to a stable state. It'll just take a little bit longer. And if we look at the root mean square elevator deflection for different positions of the payload and different payload sizes, we see that if we bring the payload all the way to the front, that is right here at the 0 point, and we increase the payload size, it increases to a point where the elevator deflection can't correct the instability anymore. But if you bring it back, it approaches a value, so it doesn't increase indefinitely, which points to the fact that perhaps we can expand the payload envelope and positioning for fixed-wing UAVs wisely without incurring in prohibitive energy costs, therefore increasing the payload capacity and implementing active controls to correct the instability that you would get without decreasing the range and the autonomy of the vehicle. It is worth exploring more. This has not included actuator rates, which are an important part in developing the actual solution space of this stability. But it is nevertheless an interesting finding that I wanted to share with all of you. I'd like to thank the Air Force Academy and Dr. Samuel Stanton for helping me with this research this spring, and the Astronaut Scholarship Foundation for the opportunity to present here with all of you today. Thank you.
Thank you. Let's take a question for Luca.
Yes.
So one thing I noticed looking at the examples of birds carrying these things is the shape of the wing is a little bit different than kind of a standard flat wing that we see in a lot of aircraft. Have you considered modifying the wing shape to more accurately represent some of the wings that we see in nature to possibly further improve the stability?
So in our current model, we only changed the elevator angles. We have not changed the wing positioning, and we consider the wing to be fixed and non-morphing. Morphing is a big area of study for bio-inspired engineering now in aeronautics, and it would require higher fidelity models with larger degrees of freedoms to look at those effects. We have considered the fact that that could significantly improve the solution space for stability without increasing drastically the energy requirements. And I think because at the moment we have a solution without the morphing, it is very compelling to see what would happen if you increase the degrees of freedom. So thank you for the question.
Thank you, Luca. Mille grazie, signor.
Thank you.
All right, we would next like to welcome Brooke Rogachuk, and she's going to talk to us about sustainable aviation fuel production from something really interesting.
Hi, as she said, my name is Brooke Rogachuk. I'm an aerospace engineering major with a minor in environmental studies at the University of Oklahoma. And today I'm going to talk to you about sustainable aviation fuel, which is kind of like the perfect little marriage between my major and my minor. So let's get into it. Air travel is crucial for driving economic growth, connecting global markets, and facilitating trade. It brought us all here today, and not to mention all the jobs it creates across the industry. However, all these wonderful benefits do not come without drawbacks themselves. The aviation industry is a major polluter of greenhouse gas emissions, accounting for 12% of the total global transportation emissions, which is about 1.8 billion tons of carbon dioxide. If that's not enough, it also adversely affects human health. The combustion of these fuels also leads to nitrogen oxide production and particulate matter, which both affect respiratory issues as well. And the production pathways and possible fuel leaks of these standard fossil-based fuels contribute to environmental contamination in terms of soil pollution and water pollution. Now that I talked about why we need it, what is it? Sustainable aviation fuel is a type of renewable resource. It can be made from biomass, algae, agricultural residues, and waste in general. SAF can reduce life cycle carbon emissions by up to 80% compared to traditional jet fuel, depending on the feedstock and production process we use. The production process often uses to minimize the types of pollutants. So we look at the different water sources we're using and making sure that the way we're producing the fuel is sustainable. Additionally, it's designed with additional infrastructure in mind, so it can be used in traditional engines today with little to no modifications. Now a little bit about my research. I use two different production pathways to create these sustainable fuels. I use gasification and fast pyrolysis, and I model them in a software called Aspen Plus. While I'm modeling them, I look at different temperatures to try to figure out the most efficiencies in modeling them. I also use waste tires in specific for my sustainable aviation fuel to help reduce waste management, as well as to create these specific fuels. While I also model them, I create life cycle assessments and economic analysis in order to determine their impacts compared to traditional fuels, and we can look at that now. We see my two technologies there in the green, compared to other values we see in literature, here in the white, compared to standard fuel at the bottom there. We see that the minimum selling price for almost all of these fuels is coming in under the standard fuel, which is very important for the implementation of these products. We also see that the global warming potential, or the potential to emit carbon dioxide, is lower for every single process compared to standard fuels, which is obviously what we want to see. I'd also like to point out there's a direct correlation. So the lower we're seeing the global warming potential, the higher we're seeing the cost. So a lot of optimization is going to be needed in order to find this middle point of production. I'd also like to point out the most common source of sustainable aviation fuel today is going to be coming from this process. That is because it has the lowest minimum selling price and the most economical. But one of the major issues with that is that this process can only use waste oils. So it can only use vegetable oils or palm oil, which contributes to the food versus fuel argument. We do not want to take food away from people who are starving, so we want to keep it in terms of waste, which is where my technologies have such an advantage over this current one. In conclusion, we can actually reduce the cost of air travel when we're using sustainable aviation fuels. We're getting a reduction in impacts across the environment, as well as we're increasing energy dependence. So we are able to produce these fuels in America, which reduces our foreign dependencies on kerosene. More optimization is needed for these products, but we're going to see a lot of that in the upcoming times. And I'd like to thank my PI, the Astronaut Scholarship Foundation, for having me here today. And I'm also happy to announce that the results of all of this publication and a lot more work is all published in the Journal of Energy Conversion and Management.
Excellent. Well, congratulations. Who has a question for Brooke?
Great presentation, Brooke. I was wondering if you thought that the economic analysis you did on your plant would be affected by either increasing or decreasing biofuel subsidies in the United States.
So I have actually a pretty big breakdown here of my economics. And what did you mean by subsidies in the United States? Sure. So if we have a difference in feedstock, I actually ran a machine learning model to determine the different impacts of different parameters. I found that the differences in the feedstock we're using does not have a huge variation as compared to the amount of fuel we're going to be producing and the location of the fuel we're producing. But when we're using corn, we can use the waste of corn, which is going to be a little bit more environmentally friendly and maybe better sustainably sourced.
Thank you so much, Brooke.
Thank you.
Next, we would like to welcome Winter Jones on lowering emissions and environmental impact from civil supersonic transport. Welcome, Winter.
Good morning, everyone. My name is Winter Jones, and I attend the illustrious Spelman College. Today, I'm here to tell you about how we can lower emissions and environmental impact from civil supersonic transport. This research is conducted at Georgia Tech. Now, let's start off with the would you rather. Let's suppose that Innovators is not taking place in Houston. We're not in Orlando. No, we're in Brazil. Would you rather get there in 17 hours or 8.5? Can I see some hands raised for 17? All right, now 8.5. Great, keep your hands up because you are feeding the demand for civil supersonic transport. But you're not alone. According to Boom Supersonic, 97% of global premium passengers are interested in flying on a supersonic airplane for long international trips. So if we know that we want to use civil supersonic transport, we must now determine how are we going to fuel these planes. Well, we are going to look at two primary fuels, Jet A and sustainable aviation fuels. Now, Jet A is non-renewable. It's derived from fossil fuels, which is what Brooke was talking about. And it also emits gas pollutants and particulate matter. The particulate matter that we are most focused on is soot. This can lead to health complications, contribute to climate change through deposition and contrails. Now, on the flip-hand side, we see that sustainable aviation fuels are renewable. They're derived from non-petroleum feedstocks, and they actually reduce the particulate matter emissions. So now that we know what fuel we want to use, we must now determine how are we going to light it. Well, that's when lean, pre-mixed, pre-vaporized combustion takes place. So we take our fuel and we're going to vaporize it and mix it with air. We're going to mix it with air such that it is lean. So if you notice there are actually more air droplets than there are fuel droplets. This is all going to take place prior to it entering the combustion chamber. Pre-mixing to lean conditions provides a more uniform chemical field during combustion, reducing the emission of NOx and particulate matter. Our first research goal is to quantify the gaseous pollutant emissions from the combustion of each fuel in a high-pressure, high-temperature LPP combustor. So this is what our emissions bench looks like here, and we have three main devices that we're looking at. Now, what we do not want for them is actually the unburnt hydrocarbons, NOx, and you can't see it, but it's actually carbon dioxide as well. Now, carbon dioxide and the unburnt hydrocarbons are going to contribute to greenhouse gases, which is toxic. We don't want that. While NOx is going to actually contribute to acid rain. And this picture that you see here is what our rig looks like. Our next research goal is to qualitatively analyze the amount of particulate matter produced from each fuel via optical particulate matter diagnostics. The first diagnostic we are looking at is natural luminosity. Now, essentially what's going to take place is this is what our combustor looks like while it's being lit. And we see that it's a lot of light emitting from this flame, right? Well, all of that light is actually soot, so we do not want a sooty flame. So we're going to have a special camera that will take pictures, and we'll be able to compare the pictures and see exactly how bright our flame is. On the flip-hand side, we also have laser-induced incandescence. Now, what will take place is this same combustor, we're going to shoot a laser through it. And when the laser hits the soot particles, they'll actually begin to heat up and incandesce. So this is what Steve was talking a little bit about earlier. And when it incandesces, we'll then do a series of mathematics to determine quantitatively how much soot is within our combustor. So I unfortunately do not have any results for you right now. As many of you guys know, research can be a bit slow at times, so we're doing a lot of the preliminary building up to actually get to experimentation, which should take place in September. These are my references. I would like to thank my family, NASA ULI, and a huge shout out to the Bernard Harrison HBCU Astronaut Group, as well as the Amelia Earhart Festival in honor of astronaut Kathy Sullivan, and of course, the Astronaut Scholarship Foundation. So in a brief recap, you learned the difference between Jet A and sustainable aviation fuels. You learned what lean, pre-mixed, pre-vaporized combustion is, gas analyzer bench, and the optical particulate matter diagnostics. Now, fire away with questions.
Very good, Winter. We have one question right off the bat.
Thank you very much for that. That was a very good presentation, obviously on a very important topic. I just had a question about how, when we're calculating greenhouse gases effects from SAFs versus Jet A, because when it comes to reducing these alternative fuels, there's still a greenhouse cost, so to say, because growing corn or any of the other sustainable products we're using still are very greenhouse intensive. Like agriculture is a very big contributor to greenhouse gases. So I was just wondering if you had any analysis that also included kind of the production costs for the fuels, not just burning the fuel, if that makes sense.
So the way that our sustainable aviation fuel is actually produced is quite different than Brooks. Ours is actually through biomass. So as she was saying, it's not as healthy as the using corn stock. But as far as the more information on it, I currently do not have that. I do know that sustainable aviation fuels is really difficult to source due to it's just a new type of fuel. But I hope to research that more and get back to you. Thank you all.
Thank you, Brooke. Thank you, Winter. Come see me later about getting me to London faster tomorrow night, please. Thank you. All right, next we have Tomas Calado, and in a nod to my mother, who was a Latin teacher, per aspera ad astra e retro. Thanks, Mom.
Alrighty, hello everyone. My name is Tomas Calado. I'm a mechanical engineering student at Washington University in St. Louis, and today I'm going to be talking about per aspera ad astra et retro, which is Latin for through struggle to the stars, and back again, because I'm going to be talking about how to ensure safe recovery of NASA's Student Launch Initiative competition rockets. So I'm a member of Woo Rocketry, which is Washington University's NASA Student Launch Initiative team. So NASA Student Launch Initiative is essentially a competition where you design, build, and launch an L2 class rocket as part of the competition as a collegiate team. We've got about 60 members. And you're judged on a mixture of engineering design, technical documentation, and flight simulation accuracy. The latter part essentially being, I like to describe it like a game of 8-ball pool, kind of like you call a pocket. We have to call an altitude before the competition, and then you get graded on how close your actual apogee or highest point in the flight is to that altitude, while at the same time also flying a spaceflight-related challenge payload, which was an autonomous UAV in the 2023-2024 season. So I'm specifically the lead for the recovery sub-team. So the competition requires the rocket to be fully reusable. You have to be able to launch it again within 2 hours of landing, and therefore it needs to be recovered safely. So I'm the leader for an 8-member sub-team, which is essentially tasked with selecting and designing the parachute systems for the rocket and ensuring that it returns to the surface without damage or risk to bystanders. So this is something that is definitely very important to any rocket competition, because this is what an L2 rocket is supposed to look like. You can see there's fins at the bottom, the nose cone, pretty clean, and most importantly, it's out of the ground. This is what it looks like after a recovery system failure. This is currently about 6 feet deep in a Missouri cornfield. Definitely not going to be reused for flight anytime soon. So that's why recovery is such an important part. So essentially, the recovery system is you'd think it might be a relatively straightforward system. You just slap a parachute on it, and then that keeps it from hitting the ground too fast. But it's actually a bit more complicated than that. So essentially, the general ConOps for the system is we start with a drogue parachute. This is essentially a really small parachute, about 12 to 15 inches across, that you deploy at apogee. We use black powder detonation to pressurized chambers to separate it, and essentially the drogue parachute's job is just to stabilize the rocket. It doesn't really slow it down very much, but it means that it's descending somewhat controlled instead of just nosediving into the ground at very high speeds. And then once we get to about 600 feet, we have a pilot and a main parachute. The main parachute is essentially just wrapped up in a deployment bag. This keeps it from getting tangled and protects it from the black powder charges. But this also means it's sometimes a little harder for it to deploy because the risk of it getting tangled in the various shock cords that come out are also folded up. So the idea of the pilot is the pilot parachute is another small parachute that essentially catches the wind on deployment, drags the deployment bag clear of all the shock cords, and then provides the force to help tense the shock cords and release the main parachute, which is typically 84 inches. We've had it as large as 120 inches, and then that's the one that actually slows the rocket down to a relatively safe speed. So to actually design the system, we base everything on the parachute size, which is originally derived from the mass. NASA defines requirements for the kinetic energy our rocket can have. Unfortunately, they make us use imperial instead of metric, so we have to keep it under 75 foot-pounds, and based on that, we can then figure out the required terminal velocity in feet per second. From there, you can use basic aerodynamic equations, just calculate the drag, and then from there, the area of the main parachute. And then based on that, you can then go back and figure out the rest of the system, what other requirements you need to, say, work with our payload. Like I said, this year, ours was a UAV that had to be deployed, so we had to make some modifications to account for the fact that we needed the parachute system to not interfere with the drone disconnecting from the rest of the system at about 400 feet, because it would suck if we had a drone that actually flew right up into the parachute, and then caused everything to fall apart. So yeah, and then this all led to our actual competition. So we did face a few setbacks in the 2023-2024 season. We had some avionics challenges that led to flight anomalies, and recovery-wise, our original system had some flaws that led to some tangling issues. That's part of the reason that we implemented a pilot parachute system, was to prevent those risks. The original design meant that sometimes it would deploy, but then the parachute would get partially tangled in shock cords and not fully deploy, so we had to make some modifications. It was a lesson learned. And then we successfully flew. This is actually from our launch at Huntsville, and we recovered our rocket at the competition in April, and we actually placed 9th overall out of about 50 teams, so it was our most successful year yet. Alrighty, so I just want to say thank you to obviously the rest of Woo Rocketry. They're all amazing people, and we couldn't have done this far without all their work. Also NASA for running the competition, WashU's McKelvey School of Engineering for supporting us, providing us resources, and then obviously ASF for letting me present here today. So I'm now happy to take any questions.
Thank you, Tomas. Let's have a question.
I actually got a question. What testing did you do in preparation for your competition to make sure that the parachute would open properly, that their descent rate would be right, and especially that it wouldn't shock load the system too much?
Sounds good. So we have the serious testing and the fun testing. The serious testing is we do a black powder test where we just go to our mentor's yard, we load it in with black powder, he has a detonator, and then we release it. And that's the serious testing. The fun testing is we pack up the parachute in a bag, someone gets in their car, we go to a big open parking lot at a mall, someone throws the parachute deployment bag out of the car, and we see how it deploys and if it actually catches the wind and is pulled out properly or not. So it can be, that one we didn't even maybe talk to NASA as much about as the black powder, but they're both really important and it gave us a lot of good info. Also, sometimes we throw stuff off of the roofs of WashU's buildings, so yeah.
Okay then. Thank you very much, Tomas.
Thank you.
I would someday love to see a video of the throwing out the window. All right. We have, we're going to give you a little bit of a different break, but we're almost done, but people are needing a stretch. So Ashley is going to lead us in a famous stretching exercise that she did yesterday. So everybody stand up. Everybody, if you can, stand up.
Yep, we're in our last home stretch, so we're going to stretch. I hope that's not too bad of a joke. Okay, so far today, we've learned about some image deblurring. So let's rub our eyes, deblur our eyes, deblur our minds, right? Winter taught us about burning flames. So it's like the fish, okay? I figured we'd have one repeat. Wow, this is so fun to watch. I just want y'all to know that. Okay, then we're learning about gases. All these gases that we're trying to burn off, right? And hopefully reduce emissions. That's a common theme. Okay, we don't want those psilocybin hallucinations. Okay, no hallucinations. And then finally, it looks like coming up, we've got some low gravity. So let's get that low gravity ready. Okay, are y'all ready for the final stretch? Okay, let's do it.
Please do indeed get rid of your gases before the gala tonight. Thank you. That's another public service announcement. All right, no. We're going to sit back down again. Everybody, we're going to proceed immediately because we have to stay on time. All right, let us now welcome Asa O'Neill for modeling and optimization of a cryogenic CO2 deposition system using computational fluid dynamics. Welcome, Asa.
Hello, everyone. So my name is Asa O'Neill. I attend the University of Kentucky and study mechanical engineering and physics, but I'll be talking about the research I've done this summer at NASA's Jet Propulsion Laboratory. So it's a long name, but basically I'm working on a cryogenic CO2 scrubber for the astronauts for human spaceflight. So a little background, carbon deposition, I'll abbreviate as CDEP throughout this presentation, or CO2 deposition. And it's basically when you take gaseous CO2 and turn it into solid CO2. So that's our method for removing CO2 from spacecraft cabin air to revitalize the atmosphere. So a little bit of a background, we'd be operating way down here on the phase diagram at about 120 Kelvin. And you're probably more familiar with the reverse of this process when you see dry ice sublimate to CO2 vapor. But moving forward, the scope of the project is to use StarCCM Plus CFD software to maximize CO2 capture and mitigate channel clogging for this carbon capture system. So this is an experiment that my mentor built. And basically the way it works is CO2 from the cabin enters from this side with high concentration CO2, or the air with high concentration CO2, and it exits on this side after depositing a bunch on these cold surfaces. So this center pipe is going to be a heat pipe long term, but it gets to cryogenic temperatures, and these are just metal fins, which I'll talk more about the geometry in a second, that get very cold and freeze the CO2 out of the air. And so my simulations are allowing us to explore new designs without expensive build test cycles, which is really, really useful in developing this technology. So I can produce, I recreated this experiment in a simulation and produced graphics such as these, where we see temperature, CO2 concentration, and more importantly, we experienced this unexpected channel clogging in our experiment. So basically, all the CO2 was depositing on the front surface, on the upstream surface of the first fin. So these downstream surfaces are doing nothing. And so this is bad because it's a very inefficient use of our surface area. And so I recreated this. This is a function, or this is a graph of ice thickness versus position. And this spike on the upstream face of the first fin is exactly what we experienced. So I validated my model from the experiment, and then I moved on to exploring new designs. And so we chose to use this fin with an involute geometry. This is set by an involute curve for a few reasons. It maximizes surface area, which is good to minimize CO2 diffusion path and remove more CO2. It also minimizes pressure drop, and it's easily integrated with a heat pipe to cool it through this center hole. The CFD is allowing us to visualize the flow and icing to inform new designs and improve this. And so I can compare, the first thing we want to know is how many of these surfaces can we fit in, because we do want to maximize surface area, but we don't want to clog it up prematurely. So I can explore designs with different numbers of surfaces, compare their outlet concentrations of CO2, and compare how they ice up. And so these are very old pictures because I had to get them released in time for the presentation. But as we would expect, more surfaces correspond to a lower outlet concentration of CO2. It captures more of the carbon, and fewer just the exact opposite. But we see similar icing if you plot ice versus position on the fin. Upstream is very preferential for ice accumulation. And so if you're not careful, you'll clog the channel pretty fast. So it's a balancing act of how many of these surfaces can you include to deposit the maximum amount of CO2 without clogging it up prematurely. And so what I've actually found since I made these slides was it's better to use fewer surfaces. So I'm actually using a variant of this 24 surface design that's shorter in the direction of flow, so thinner in this direction, and just use a whole bunch of them in an array, and you get pretty efficient CO2 capture. And so I've actually made an array of fins that meets the target CO2 capture requirements for a 4-person crew in my simulations. So the context and meaning, this is a compact, reliable system that would have reduced maintenance requirements, making it a potential successor to the carbon dioxide removal assembly you see here, or a 4-bed CO2 scrubber you see here on the ISS. It would replace consumable adsorption systems, which makes it ideal for long-duration missions since you don't have to pack consumables. You can also use it for in-situ resource utilization and trace contaminant control. And the impact of this research and future expectations is to integrate it with a system more like this that incorporates regeneration to increase your heat exchanger efficiency and lower your power requirements. So that's my presentation. I would like to acknowledge my mentors at JPL, especially Diego Fonseca Flores, and open it to questions. Thank you.
Fantastic job. We've got time for one question.
And so as that CO2 accumulates, how often do you have to replace that or clean it off, and what do you do with the excess?
That's a good question. So the way this would work is we would have 2 of these systems, and they alternate between depositing and sublimating. The research at Ames has shown that it sublimates much faster, so deposition is what limits you. And so the system I designed, you'd have 2 of them. One would deposit for 45 minutes, then sublimate for 45 minutes, and then the other one would be doing just the opposite. And what was the latter part of your question?
What do you do with the CO2 after?
Yeah,
what do you do with the CO2 after it accumulates?
Yeah, so you would sublimate that somewhere else for a downstream chemical process, which I'm not entirely sure what they want to do with it, but I do know there's a use for it. Okay.
Great job. Okay, next up we have Ryan Lewis, who's going to be talking about a novel apparatus to stimulate low-gravity particle dynamics. Welcome, Ryan.
Hi, everyone. Thank you for coming. I'm Ryan Lewis. I go to Utah State University, and I study mechanical engineering. I study with Tim Burke, and I work in the experimental fluids lab. So to give a little bit of context, if you don't know what experimental means in the context of engineering, it really just means adult Legos. So that's what we're working with here. And to provide some imagery to why this matters, I want you guys all to imagine you're wearing clothes, okay? I hope I haven't lost any of you. But now I want you to imagine those clothes are made of sandpaper. So anytime you move, there's abrasion and there's wear. And on top of that, every time you breathe, you're breathing in really small, sharp glass shards. Well, welcome to the moon and Mars. This is a huge effect. In fact, it's considered the #1 issue in long-term operations on the moon and Mars. On Earth, we take it for granted how good we have it. We have a lot of erosion that tends to round things out and smooth things out. So we don't really get much abrasive material. Here's on the bottom, right here, is a micro picture of the dust or the regolith on the moon. You can see it's really sharp and jagged. And this is a big issue. So we see in fluids, we call it multi-phase flow, right? A gas, and essentially think like a gas and a solid. We see dust getting stirred up when lunar landers land on the moon or on Mars during the weather events, and including landing events. Well, this is a big issue. It gets on astronaut suits, wears them down, and as well, here's an image of Opportunity, and its mission was actually cut short by dust covering these panels. And NASA isn't sitting on their hands. They're not dumb. They recognize the issue, but it's really difficult to understand how this dust is behaving and why it's behaving the way it is, because gravity plays such a key role in such things as like settling effects. The problem with this is gravity is so integral to how settling effects behave and other effects that we have to essentially simulate lower gravity to understand how these things work before we can make preventive measures. So some of the ways we've tried to study this before are parabolic flights for microgravity, same with the ISS. Both are really expensive though, and so the volume of research you can get out is somewhat small comparatively. Another way you can try is through drop towers, where essentially you let an experiment in free fall for a few seconds. But due to the limits of how high you can really build these drop towers, we don't get very long experiments, and there's certain effects that take certain time scales to start up, and drop towers can't study those. And then last is CFD. CFD has a lot of promise, but the problem, just like other models, is you need a lot of good data to train your models on, and that's the problem we have with low gravity. We don't have that data yet. And so what we're trying to do before we study this, we really want to make an approach that's affordable, not just for us to study this, but we want to create a platform for other people to study this as well. And it gets into a little bit of nitty-gritty stuff. The physics majors, please come talk to me. I'm sure you could teach me a little bit about this, but essentially what we're doing is we're giving a surface charge to particles, and then we're dropping them into an upward electric field, and it's pushing on them. Surface charge is just like, think of rubbing a balloon on your head, right? It becomes staticky. That's exactly what we're doing with these little particles here. This orange is the Coulomb force that they get from being charged in an electric field, and the net force, we can say, simulates a lower gravity. So how do we do this, right? If it was so simple, people would have done it before. Well, first, and believe me, it sounds simple, but it's really difficult, it's creating a consistent stream of particles. It has to be really small and dispersed. To do that, I'm just going to cut to the chase. We use vibrating motors to prevent clogging. And then as well, we use a mesh to disperse the particles, and we have to have a carbon fiber funnel to disperse any charge these particles are building up while they rub against each other on the way down. Next, they enter the charging station. We use something called corona discharge. This occurs when you run a really high voltage through a really small cross section. So it's a fancy way of just saying like high voltage through small wire. This creates ionized air, and as these particles fall through, they get bumped into by these ions and they receive a surface charge. Now to the really cool part, the adult Legos. Here we see these particles. They're coming in, they're falling. Here's our dispersed stream. And right around here is our wire with the high voltage. And they start to pick up these ions and receive a surface charge. And as they receive a surface charge, they're pushed by the electric field, and we can see them curving here. Here's an annotated slide showing such. It's really cool to see some of these particles, especially as they're near the stronger electric fields, especially around the ionizer wire. You can see them fly off, and some of these high-velocity particles slam into the grounded plate and bounce. So this has been a really big task, just setting it up this far. And the final part is, how do we measure these Coulomb forces? How do we know we're getting the charges we actually want? Well, and simply, we just have two copper plates, we run an electric field, and we watch how fast these particles are moving, and we can get their acceleration and thus their surface charge and Coulomb force. So these are the results. They just show, yes, the particles are receiving charge. They are feeling a Coulomb force based on their acceleration. And in conclusion, dust is a really big issue. In fact, one of the key defining issues in setting up long-term operations on the moon and Mars. Previous experiments are really expensive, and so we're trying to devise a new platform to do such. The future work, we're very close to validating this. The future work is to orient the test section so that it's pushing upward on the particles, thus simulating low gravity, and once we've demonstrated that, we'll finally add actuators on the side to induce turbulence and study these turbulent flows in low gravity. I just want to say thank you guys. Seriously, if you have any questions or if you want to do anything, please reach out to us. We'd love to collaborate or just talk. But thank you guys. I really appreciate you guys as a ASF family, and I want to reach out. And I don't know if my professor's watching, but if he is, thank you as well. I really appreciate all the work you've done with me as well.
Great job, Brian. We have time for one question.
All right, this really isn't much of a question, but it kind of reminds me of like a vacuum. If I'm wrong, correct me if I'm wrong.
Could you explain a little?
Yeah. So to me, like the problem was like there's dust covering the panels, right? So you kind of want to figure out a way to get the dust off. That's just my interpretation of it.
Yeah, I could provide a little bit more context maybe.
Yeah. The
real issue is in application, right? Not just in research. The real issue is dust tends to stick to everything. Talk to me afterwards. I don't want to just sit up here and go on one of my tangents, but there's some static charge on the moon with dust. It sticks to everything, but the problem is a lot of times when we're trying to prevent this, it needs a key understanding of how dust works, and we just don't know that because we're subject to Earth's gravity, right?
Okay.
Is that what you're asking?
I mean, kind of. I was trying to...
Let's talk.
Yeah.
Let's talk about that.
Let's connect.
Thank you, guys.
Thank you. Let's talk about dust. later. But now, Abigail Glover is going to talk to us about a whole bunch of stuff regarding moon stuff and dust and other things. Welcome, Abigail.
Hi, everyone. My name is Abigail Glover. I am a mechanical engineering student at the University of Central Florida, minoring in mathematics and astronomy. And my title is very long, as you can see, but real quick, with a show of hands, how many of you are excited that we are going back to the moon? Awesome. Just from looking around, you can see that everybody is eager to get back there, but my focus of research looks specifically at how we're going to be there long term. So I know we all come from a variety of backgrounds, so I want to make sure we're all on the same page. Today I'm going to be talking with you about how testing lunar hardware in fake moon dirt is going to prepare us for long-term lunar habitation. So lunar regolith simulant, or the fake moon dirt that I'm referring to, is key to successful hardware testing. Because the Apollo missions brought back a relatively small amount of samples, engineers and scientists here on Earth need large amounts that we can use. Thus, the need for a fake space dirt industry became relevant, with the world's leading producer, Space Resource Technologies, housed in the same building as where I work. In fact, if you want to talk to me more about the manufacturing side of things afterwards, I actually started as a manufacturing engineer to create these fake dirts. But moving on, for my research, I'm looking at primarily two different topics between RIDER, which I'll talk about on the next slide, and the Sparta toolkit. Now, why is this important? This is important because, I'm sorry, I'm getting a little choked up, to prepare for long-term lunar exploration and habitation by being able to simulate all of our tools and equipment here on Earth. Now, RIDER, or Regolith Interactions for the Development of Extraterrestrial Rovers, or this big bin you see here, is a 4 meter by 1 meter regolith bin located at UCF's Exolith Lab. It provides testing capabilities to examine a single rover wheel on a linear actuator so that we can simulate the load that the wheel would feel as if it was on the moon as part of a whole rover with a full payload. Me specifically, I was in charge of designing the environmental control systems as well as the motor box housing. However, I was curious about how environmental controls were actually impacting the moisture content in the regolith simulant. If you've been to Florida, you know it's hot and humidity does not bode well with the regolith simulant. So my results so far have shown some very interesting results. I ran a simulation to see how the airflow was directly impacting the regolith simulant and the moisture content. And my results actually showed that my model was consistent with the results that I was getting, and with the main takeaway from this research being that initial compaction conditions actually affected the core samples that we were getting and their moisture content. So what does this mean? This means that if you are in the bin sweating, and it's a really high humidity in that area, and you compact the regolith, that moisture is going to stay under the surface level, which affects how we're testing our hardware here on Earth versus what we'll experience on the moon. So for impact and expectations for the future, this research has the potential for continued work, and both topics have importance in various applications. As a couple people mentioned, in situ resource utilization is huge, and it describes the geomechanical properties of simulant on Earth to better understand hardware requirements and actually extracting the resources on the moon so that we don't have to send that much up there when we eventually go. Additionally, terrestrial testing procedures, by looking in a smaller bin here on Earth, we know that we can do larger scale testing as opposed to just the small scale testing. And then finally, baseline data for the moisture content levels in RIDER and the Sparta toolkit gives us data that we can then compare when we actually do go to the moon and Mars. And then we can compare that data and see how we can improve our hardware here on Earth over time to reduce costs and additional testing that may be needed in the future. So thank you very much. I'd like to thank all of the partners that I've worked with and ASF, so I'm open to questions.
Thank you, Abigail. Let's go ahead and take a question.
Great presentation. I was just wondering if you accounted for like moon dust or rocks or other surfaces as example in the last presentation as well in affecting the hardware.
So the fake moon dust that we accounted for was the simulant that we used from the lab. The Ryder bin specifically was filled with about, I want to say 2 to 4 tons of the simulant, which is supposed to replicate what we would experience on the moon. As far as what I was looking at for the moisture content sampling, I was taking samples of that regolith and drying it out to see how much moisture was being retained in it. Ryder does have the capability of looking at the wheel interactions with the particles, which was actually part of my initial proposal. However, as Ryan was explaining, gravity here on Earth does affect the particles much more differently than it does on the moon. So being able to examine that portion wasn't feasible at the time, but it's great implications for future work, and we're hoping to look at that down the road.
Super. Thank you so much, Abigail. Next, let's welcome Julia Fancher on modeling tidal disruption events. Welcome, Julia.
Hi everybody, my name is Julia Fancher. I'm a physics and applied mathematics major at Syracuse University, and I research high-energy astrophysics, specifically something called a tidal disruption event, or TDE. So a TDE occurs when a star gets close enough to a supermassive black hole that the tidal force from the black hole overcomes the star's self-gravity and rips it apart. About half the debris stream you see on the right there is bound to the black hole, which means it's going to orbit the black hole and eventually fall back onto it. This fallback process creates a luminous flare that we can see from Earth, and this is what makes TDEs really cool, at least in my opinion. So TDEs often occur in otherwise quiescent galaxies, which means there's not a lot of other activity happening there. So TDEs often are our only window into the stellar populations and black holes in the center of faraway galaxies. And with the completion of the Vera Rubin Observatory in the next year or so, we expect to see the number and the rate at which we observe TDEs to go up drastically. And so it's really important right about now to have an accurate way to model and interpret these light curves. And we have 2 main ways of doing this. One is to use a numerical simulation, which is highly accurate, but can be incredibly computationally expensive and time-consuming. So if we can, we'd much prefer to use an analytical or mathematical model, which is a lot simpler and faster, but can make incorrect assumptions about the physical processes happening. The typical analytical model we use for TDEs has been around since the 1980s, and it's known as the frozen approximation. This model says that when we reach the tidal radius, so the point at the bottom here, where the tidal force from the black hole is equal to the self-gravity of the star, at this point, we assume the star is in free fall around the black hole, which means that the pressure and self-gravity of the star are considered negligible. We don't consider them. And this means that we can assume that the orbital energy of the star is frozen in. And so for any given point in the star, we can predict how long it will take for the material to fall back onto the black hole, and therefore we can get a fallback rate and thus a luminosity. So a paper in 2009 said that for any given star, we should see an energy distribution that looks like this dashed line here. So one nice smooth curve around the center. Then they ran a simulation to test this, and they saw mostly what you'd expect with that solid line there with the central peak. But it also has 2 smaller peaks that they didn't expect, and they called those wings. These wings tell us right away that the frozen approximation is missing something. And this paper said that this is due to pressure, so shocks are propagating through the star as it's being destroyed. But since then, we've seen in partial disruptions where the core of the star survives the encounter with the black hole, the core's gravity can greatly impact the fallback rate. And so we said, what if even in a complete disruption, the self-gravity still has an important impact? What if self-gravity is responsible for those wings? So to test this, we ran 2 sets of simulations with a code called Phantom. One where we leave self-gravity on the entire time, like in real life, and one where we turned off self-gravity at the tidal radius, as in the frozen approximation. So if the frozen approximation is correct in saying that we can ignore self-gravity, these 2 simulations should give us exactly the same results. And then just to make sure that what we were seeing is actually a physical representation, we ran the simulations with self-gravity on the entire time at multiple different resolutions, ranging from 250,000 particles in the star, which is comparable to the 2009 paper, up to 128 million, which is the highest in resolution of a TDE. So what we see when we turn self-gravity off at the tidal radius is basically exactly what we expect. So this dashed line here is what we predicted with the frozen approximation, and then these colored lines are what we calculate from the star after it's passed the tidal radius. So you can see that aside from some numerical noise, these curves are exactly the same. The energy is frozen as you expect. But when we leave self-gravity on the entire time, we see something completely different. So within 35 minutes, this stream has evolved and the central peak is almost entirely gone. And looking at later times and moving to a high resolution to make it a little bit prettier, we can see that after about an hour and a half, the central peak starts to reform. But after about 30 hours, the stream stops evolving, and it never reaches the height that it originally was. And so this tells us two things. One, the frozen approximation does not predict the evolution whatsoever. But two, and more importantly, it can't predict the long-term effect of this evolution. And so the effect is actually this. So this is the fallback rate calculated as it's evolving. And so the frozen approximation tells us that we should see something like this blue curve all the way on the right. What we actually see is the purple line, which is conveniently covered by the dashed line, which is actually what we see from simulation. And so if we're using the frozen approximation to interpret the light curves from TDEs, we're going to be interpreting them wrong. And so we need a new analytical model that includes self-gravity in some way to accurately interpret TDEs, which is what I'm working now, and we'll hopefully have finished soon. Thank you all so much for your time and attention, and I will happily answer any questions.
Thank you, Julia. Let's have a question for Julia.
Hi, Julia. Great talk. I'm a little bit curious about the star that you're simulating. I would imagine that the mass of the star, and particularly its place along the HR diagram, would have an impact on its puffiness, its ability to be stripped by the black hole. So can you tell us a little bit about the star that you're simulating, and if you have intentions to simulate different stars of different masses and evolutionary stages?
Yeah, so I'm doing a simulation here that my advisor likes to call a vanilla TDE. So it's the most basic way. It's a polytropic star, which means it's a simplified density profile. It's not really realistic for anything higher than about 0.5 solar masses. But what I've been doing recently has been using stellar evolution code to use actually correct density profiles to use those for simulations. And so what we actually see when we look at realistic stellar structures with high mass and older stars that are more evolved and have a more centrally concentrated core, the self-gravity has an even greater effect. And so the frozen model is even more wrong in that case.
Thank you, Julia. Let's avoid puffy black holes. Charlotte Moore is here with us now, restraining merger time of Centaurus A. Welcome, Charlotte.
So hi everyone, I'm Charlotte Moore. I am from the University of Central Florida, and today I'll be talking to you about constraining the time of Centaurus A's merger by looking at the contents of its stellar halo. So I actually want to start out and introduce my team. Ooh, that's a little off. Eric Bell is my PI over this summer. Riley was another undergrad working on the same project. Dan Kelson at Carnegie Observatories did all of our data reduction, which I'm very grateful for. And Ben Velguth is a recent UMich graduate who acted as a mentor to me. So, when we look at galaxies in the sky, what's actually keeping them together are these clumps of dark matter called dark matter halos. The interesting thing about dark matter is it only interacts with other types of matter through gravity. What that means is two different dark matter halos can become attracted to each other. And when this happens, the galaxies residing within these halos collide in what we call a merger event. The issue with merger events is when we're talking about the history of the universe, they happen on very short timescales, which means if you're looking at the main body of the galaxy, you really can't tell anything happened. Where we can look are at the stars that were flung out during this merger event in the outermost regions called the stellar halo. Question is, how hard is it to see the stellar halo? So, I have a little example. That's the Milky Way right there. So in that box, which is about 1,000 square degrees, is the constellation Centaurus. So we're going to zoom in. That's Centaurus. There we go. Okay. And right above the star Omega Centauri, in about 4 square degrees, so 1,000 to 4, resides the galaxy Centaurus A. That's how far we have to zoom in order to individually resolve stars. So a little about Centaurus A. This is a nearby galaxy which we already know is the result of a merger due to the metallicity ratio as well as some of the structures we can see in the stellar halo. What we don't have a good constraint on is when this merger occurred, which is why we go back to the stellar halo. When stars like our sun die, they end up becoming very cool but very massive, which results in very luminous stars called red giant branch stars and a variation on those called asymptotic giant branch stars. We have very good constraints on the lifetime of these stars, which then allows us to date the merger. So, We ended up taking observations on the 6-meter Magellan telescope in Chile, and we took a total of 20 fields in two different bands in the infrared, which covers the entirety of Cene's stellar halo. So I'm just going to focus on one field there in the very center. So we need to take this, perform data reduction on every single chip, and then determine individual stars within these chips. So we're going to just focus on chip 2 for right now. That's the reduced data. How do we actually tell what is a star? We use a process called photometry. Specifically, we used a software called DALPHOT. And by basically telling this software, this is the distribution of the luminosity of what we think an ideal star candidate is, DALPHOT will then reject things that it doesn't think is a star candidate and identify individual stars. So these are only a few of them. In this total field, we found about 17,000 stars. What can we actually do with those? So earlier, the HR diagram was mentioned, and essentially this graphically shows the evolution of stars. So you can see up there, that's where our RGB and AGB stars reside. We're not actually making an HR diagram, but what we can do is make color magnitude diagrams. So by looking at the brightness of the stars in different bands, we can determine those stellar evolution. So that branch right there is what we found from our stars. But we still have a lot of work to do. This is just preliminary results. We need to make sure that the stars actually match up with other surveys that we found of smaller fields, and from there, making sure all our magnitudes are correct. But once we have those CMDs perfected, we can actually make a list of every single star in Centaurus A, and then confirm the merger time. So I'd like to acknowledge the University of Michigan and NSF for funding this research opportunity, as well as ASF for hosting. And if anyone has any questions, now's the time.
Thank you, Charlotte. Who has a question for Charlotte?
Great presentation. I'm a mathematics major, so fields mean something very specific in the world of math. So how did you constitute what a field meant in this context?
Okay, so I also do math. So fields there are very different from fields here. Fields are basically just like, it's a field of observation, so like what you're physically observing, sometimes also called pointing. So it's not related to like field theory where like, it has all of these like certain rules and it's on a set. So 2 different things.
Cool. Thank you.
All right. Thank you so much, Charlotte. All right, now we would love to welcome Ashley Tarrant from Light to Mass, and I'll let her fill in the rest. Welcome, Ashley.
Hi everyone, my name is Ashley Tarrant. I'm a senior at The Ohio State University, and I'd like to talk a little bit about my work that I started last summer at the University of Hawaii, where we calibrated a relationship between the light given off in this object called an AGN and how we can use it to estimate the mass of the central supermassive black hole and why that's important to astronomers. So, first of all, we'll talk about what an AGN is. You should know that in the centers of all massive galaxies, there is a supermassive black hole, even the Milky Way. And in about 10% of these, you have an accretion disk here, which is basically gas that is falling into that black hole because of gravity. So you can imagine as that gas is getting closer, those particles are rubbing up against each other. They're emitting a lot of heat and energy and light. And what's interesting about these objects is this is in the very center of these galaxies, but it can actually outshine the entire rest of the galaxy, even with all those stars and stuff. So they're pretty interesting, but not everything is well understood. So the reason we're interested in AGN is this very central region can actually influence the evolution of the entire rest of the host galaxy. And the key thing that we need to understand for this process is the mass of that central supermassive black hole, because that's going to tell you the relevant physical and temporal timescales for the evolution that we're interested in. So something I didn't mention about AGN is across every wavelength in the electromagnetic spectrum, they basically get randomly brighter and fainter over time. Now, other studies have shown that we can measure the timescale over which this happens, and it actually correlates with the black hole mass. This is good because the black hole masses are very difficult to measure, it's very expensive, and it requires a lot of observation time with current methods. So if we can take this other parameter, this variability timescale, and correlate it with the mass, then we can efficiently get a lot of AGN masses and help inform about that evolutionary process. Now, the previous studies which have done this have done it in a way such that the AGN community doesn't really believe them very well. So they've used telescope data from several different surveys, or they've used black hole masses that we since have better measurements of. So my work sought to calibrate this relationship by using the most precise mass measurements we have available from the AGN black hole mass database and light curves from the All-Sky Automated Survey for supernovae, also known as ASSASSIN. So by taking the most precise masses with a homogeneous data set, we can mitigate biases in calibrating this relationship. So this is just an example of what that data set looks like. So here you can see the random brighter and fainter that I was kind of talking about over time here. So the reason we want to use ASSASSIN to measure variability like this is because we have over 10 years of data at a very, very high frequency. So ASSASSIN is actually an all-sky survey, meaning almost every single night it takes a picture of the entire night sky. And it's been doing this for 10 years. So this is a really, really great data set to characterize this variability. So what we do is take the light curves for all of the objects that we're interested in. We run them through a mathematical model called a damped random walk process, which tells you about how long these fluctuations take and also how tall they are. And then we see that they are indeed correlated with the mass. So this is awesome because these axes are measured 100% independently from each other. They have nothing to do, yet this correlation exists with a p-value of 5 × 10⁸. So there's really no doubt that these things are correlated. What's more interesting is that our relation that we've since measured has a scatter of 0.55 dex, which is comparable to existing scaling relations that are more difficult or more costly to obtain. So by simply modeling ASSASSIN light curves, we can get AGN supermassive black hole masses pretty much as precisely as the other more difficult relationships. So that's exactly what I'm now doing. I've selected 16,000 AGN light curves and I'm running them through our model. And so far I've estimated about 300 more AGN masses. And then just as a quick check, oh, and here I'm just showing a histogram of the masses that we have so far. And we're also checking that our tau, that's our timescale measurement, correlates with some other galaxy properties, and it does, so we're on the right track and the results are looking good. So to conclude, what we've done in this study is a careful calibration of the variability timescale and mass of the supermassive black hole in AGN. We've shown that this relationship exists with a relatively low scatter, and that means that the AGN community can now use this to go and measure other AGN masses and inform about how that will affect the evolution of the galaxy. I'd like to thank my mentors, Dr. Benjamin Shappy and Jason Hinkle, and the ASF for allowing me to present here. So I'm happy to take any questions, and thank you.
Thank you, Ashley. Who has a question for Ashley? There we go.
Hey, Ashley. Thanks for the great talk. My question is, because I'm not as familiar, how are the black hole masses in this field calculated? Does it come from semi-classical thermodynamics, or how do you actually measure these black hole masses?
Yeah, so this is actually super interesting. So if anybody wants to talk more about this later, I'm happy to. But most of these masses are measured through a method called reverberation mapping, where the AGN, so there's a light flare in the middle of the AGN, and then you can track the delay time to another region of the AGN. Maybe if I can show here. Okay, here, so a light flare here, and then it gets re-emitted in the broadline region over here. You can track that delay time. That gives you a light travel time, which can become a radius. And then you can calculate the velocity of these clouds from the Doppler shift, and then using dynamics, that will give you a mass. That's how most of them are measured. You can also track the orbits of stars or gas that are going around it. It's really interesting. I'm happy to answer more questions, but yeah.
All right, thank you so much. All right, partner, make the drum roll. Last, but certainly not least, Jenna Karczewski, Revolutions in Astrophysical Research Using the Infamous AI. Welcome.
Hi, everyone. Well, now's your last chance to wake up, so thanks for bearing with us for the entire conference. But as we said, I'll be talking about how we can use AI in astrophysical research. My name is Jenna Karczewski, and I'm studying astrophysics and computer science and data science at the University of Wisconsin-Madison. And so I'm an astronomer by practice. I work with a lot of astronomers. I get this question a lot. What is AI? And a lot of us may be familiar with this through pop culture references. I had to fit a Star Trek reference in here because my dad's in the audience. But not all AI is evil killer robots. Modern AI maybe looks a little bit like this. I don't know if any of you have ever used ChatGPT to generate images, but I asked it to generate some photos of astronaut scholars, and that's what it gave me. But generative AI can be applied to any kind of data set, like celebrities, or there's a famous data set called CFAR10, which is planes, trains, automobiles, frogs, and all that stuff. But what if we applied AI to scientific data? In particular, I work with molecular clouds, which get their name from being comprised mostly of molecular hydrogen. They're just groups of gas and dust out in the ISM, or the interstellar medium, and they kind of work like pairs of polarizing sunglasses, where the dust grain actually preferentially blocks out certain wavelengths of light based on their size and shape, and we can observe them using an instrument called a polarimeter. So here we actually simulate a bunch of these molecular clouds to use as training data for our AI model, and it essentially learns the relationship between something we can observe, which are these polarimeter quote-unquote observations, and something we can't observe, which are magnetic field maps. And magnetic fields are really important in molecular clouds and in the universe in general because they're ubiquitous and important in a lot of processes like star formation. So we've trained this AI model to essentially learn the relationship between these two. We use a conditional Bayesian framework, if you know what that means. If you do, you're a big nerd. And we actually, I got a laser pointer, we condition on the observations, and here's the ground truth from the simulations. And our AI model does a pretty good job at reproducing what these look like. And I use a framework called denoising diffusion probabilistic models, keyword being probabilistic. So we can actually get uncertainties on these measurements of seeing this particular instance of or output from our diffusion model. And we can actually apply this to real observations, and I haven't shown that on the slides here because it's quite preliminary work, but that's something that we eventually can do. So that's my work that I did a couple summers ago, but the work that I've been doing this summer is dealing with strong gravitational lensing. So this happens when you have a background galaxy that passes behind another galaxy or galaxy cluster comprised mostly of dark matter, and it gets magnified and multiplied. And you can actually, with the help of AI, disentangle these two. So I don't know if you can see this very well on the slides. You can do this analytically, but it takes, in complex system, it takes like hundreds of millions of compute hours. So you can actually use AI to build a prior on your background sources and disentangle them and reconstruct the background galaxy from this warped image. My job this summer actually was to understand the nature of the dark matter structures in the middle doing the lensing. And I don't have a picture of that because it's dark matter. But I was working on that this summer. I'd also just like to take a moment to emphasize that these are just a couple test cases of how we can use AI for good and for science. And I would love to talk to any of you about how you can use AI in your research, because odds are if you're working with data, which is literally all of you, you can probably use AI to help your research. And I'd like to take a moment to thank the ASF for having us all here. And my collaborators, and all of you, again, for sitting through that entire conference. Thanks for staying awake for my presentation.
All right, thank you, Jenna. All right, let's have a question for Jenna.
All right, so I had a question. Right now, it primarily looks like you're training your models on like very strong lensing cases. Is there any plans to maybe branch out to doing more weak lensing, or have you guys already considered that?
Weak lensing isn't necessarily what we want to do. Weak lensing is much, much harder to detect. And we have investigated models where we add additional subhalos, and that just increases the dimensionality and number of parameters that we have to deal with. So that does take a bit of time. Even in the accelerated AI models, it does take additional time to process those. So thank you.
Thank you. Give Jenna, last one. Awesome. All right, thank you so much. Well, we've had 3 amazing sessions and 3 amazing opportunities to hear unbelievable things that everybody's doing. So I just want to give you a little recap before we close off. So let's talk about some of the things that we've learned in the last 2 days. We've learned that it's bad to crash rockets. We've learned that quarks get lonely. We've also learned that water is largely non-flammable. We've learned that semiconductors get dopey. We've learned a lot about lasers. Ashley and I have been talking a lot about lasers. Lasers like to excite things. They like to be shot at, and they like to shoot at people. We've learned that llamas could go to space eventually. We've learned that dark matter matters. We've learned that dispersing gas really is a good thing. We've heard about rats hallucinating and how we get them not to. We've just talked about halos. We've talked about fake dirt as an industry. And we've seen some airborne goats. Now, the most famous thing that we've learned is, wait for it, voles can be promiscuous. So I want to thank ASF. I want to thank Caroline for giving me this opportunity. I want to thank my fabulous partner, Ashley. Stand up, Ashley. Ashley keeps me sane, which is no easy task. So I love working with her, and we've had that privilege for several years. So thank you. I am in awe of all of you, and I will just leave it at thank you, Caroline. Thank you, Justine. Thank you, the whole ASF team, for making this happen and so smoothly and wonderfully. Are you loving this? Yes. So thank you all again, and I'll just leave you with my new catchphrase: the world awaits your brilliance. Thank you so much.
So Jenna, what you don't know probably is astronauts use AI all the time. It's an unfair advantage to winning a cocktail challenge, actually. So if you met Chris Ferguson on Thursday evening, I know some of you scholars got to spend some time with him. He actually is a reigning champion of a cocktail challenge that we host in the spring, and he generates some interesting raps with ChatGPT. So next time you come down to visit with ASF, you come to well, I don't actually invite you to the cocktail challenge, do I? But you all somehow like to sneak in. So we'll see you there, and you can learn more about his ChatGPT stylings. Well done, astronaut scholars. Another round of applause for all of you. I get the fun job of running through some housekeeping items. Scholars, give your scavenger hunt sheets to Janelle. Janelle's in the back. Everybody look at Janelle's tiny little thing back there. Headshots for scholars in Salon DEF from 1:15 to 2:15. You probably know if you have signed up for that. Are there any slots left today? Sold out. Scholars, tonight, you come gala ready. Do you know what that means? Be all dressed and fancy and ready to go. Meet in the Crystal Ballroom at 4:30 p.m. What time? 4:30. Good job. And then we have a little walkthrough and I think a big photo op for you guys. So please be ready and be on time. For everybody attending this evening, the reception starts at 5 o'clock here in Marina Plaza, and then the gala will start at 6 o'clock over in the Crystal Ballroom. And I believe that's it. Well done to the 27 that went today. Well done to everyone over the course of 2 days. Thank you for being such an incredible and engaging audience. And another huge thanks to our moderators, Carol and Ashley. And our little unsung producer of our tech conference is Janelle Miller, for our program manager from our team. She collects all the presentations, she reviews them, she helps make sure everybody gets all their questions answered about their presentations. She works with our AV team. She does a fabulous job. Thank you, CCR, for running a good show. Always appreciate some good AV at my events. Thank you so much, and we'll see you all this evening.